for the predictors that are, in this case, PET, is changing. Yeah. That was just statistical intuition.
Yeah.
I think I just want to sort of
no, I think
put a little finer gloss on that.
There's no question that variation, in rainfall, both over space and time, is going to make a big difference. But I think that just knowing about that isn't going to be enough.
And I don't want to get too hung up. You've got a bullet, but it was just to summarize a bunch of different things, so it's okay.
Okay. Okay, so the main point of this is just that it's been really hard to get these cohesive data sets about PET or drought indices that are that sort of run on the same quantitative scale between the past and the future, so that you could estimate a model based on past data and then make predictions based on that same covariate in the future, which is what all these statistical models have to do. And one of the reasons is that this Monteith method of calculating PET requires more than just other, and Mike's going to tell us about why that's so important. But those other variables aren't downscaled, and so it's not easy to just have them. So you can go all the way back to this raw GCM level, but of course it's pretty coarse in terms of the spatial resolution. Richard Seeger's team didn't derive SPI data at about a 1-degree latitude, longitude grid. So that's something that our group is looking at using. And then even the historical SPI data, for those of you that work in Colorado, might be quite coarse, even at a 0.5-degree grid. And then another thing I'd like to say is that actually unstandardized P minus PET may often be much more useful for especially anyone studying plants, for example, because if the way you're organizing your GIS layers is to take the mean of a given variable over space, you're going to get, if you're using SPI, you're going to get a mean 0 everywhere. And so it doesn't capture variation in space, it just captures variation in time at a given location. So it sort of says how wet or dry is it relative to some baseline that you've defined in the historical period.
We're going to have to make up a little time to start time.
Okay, this is my last slide.
Great.
And so what I wanted to say for the workshop is just to try to introduce us to the basics of PET and water balance, and to try to figure out what are the best practices given the currently available data. And I think, to some extent there might be some trade-off between the PET formula and the spatial resolution, or we'll see how that gets resolved. And then from the ecologists talking to the climate scientists, trying to identify needs for future data products that would really suit our needs well. So I guess that was all that I had to say, and I don't know if probably since we're running over, it doesn't make sense for people to jump in and talk about how their needs are different, but
maybe just a few questions. I'll work on getting Mike's slides up, and that way, in the meantime, you can check on that.
Yeah.
And I need to find a better place to sit where I can both write and type. Do you want to come down here?
And you can squeeze next to Joe, and I'll just sit over here.
All right. Thanks.
Or I could just sit with you. That's fine.
Okay, does that work?
Well, let me get Mike. Joe.
Does anyone have any other questions? Does that make sense? Any, from the ecologists sort of gut responses about whether or not this might be relevant for you guys?
Well, the PET that you're looking at here, 27 the whole year.
It's calculated sort of in any given month. So in this example, I'm using May P minus PET sort of that goes back 12 months. So it looks back for a year in the past.
Yeah, I would be interested in a seasonal PET, seasonal disease from bioclip, for a particular season. If you can do that, it would be.
So you can do that with some of these, in that there's, you essentially have the value for each month. So you could presumably take, average over the summer, over the spring, or whatever you're interested in.
Why did you pick June to May?
because the response variable is measured in May.
Okay.
And so it's just sort of the last calendar year. I actually haven't been using 12-month SDI in my model. I've been using 24 months, but just because it's I think easiest.
So that's May pond count.
Yeah.
Let's let Mike talk. I think we got take care of this in 15 minutes. We're close to becoming that. We're only 5 minutes off schedule. Do you have a? I don't have a pointer.
No, I don't. Actually, I got those slides.
Okay.
Okay, so I'm going to talk about ET and evaporative demand, and I'm going to try to use those words. And when I say ET, I mean actual ET. That's the actual flux, not potential ET. And when I mean evaporative demand, that's potential ET. And I think there's a lot of confusion between the terminology amongst all the different terms in ET work. So I will use ET and evaporative demand. Yeah, I want to talk about why you shouldn't do this. Spatial variability, temporal variability and trends. And there's a bunch of papers that this refers to, and if you want, I can give you those papers or email to you. Okay, so really high level, what's background on ET? Actual ET is constrained by three things. You know, it's a radiative driver, a meteorologic driver, which is well, I'll get to it, and the hydrologic, the presence of water to evaporate. So the radiator driver, basically you estimate an energy balance function. It's constrained by the energy balance, primarily solar radiation, also long-wave radiation, and ground heat flux. The meteorologic driver then is the effective mechanism, the wind speed, the diffusion of vapor into the atmosphere, and the ability of the atmosphere to drive that vapor away, and the humidity gradients. And then the hydrologic driver, which is the availability of water to evaporate. And we never know the hydrologic driver, pretty much. It's unknowable. That's my main reason why I look at evaporative demand rather than ET, because evaporative demand removes the hydrologic constraint. It always says, we're going to assume, given that we know what the radiator driver is and the meteorologic drivers are, we're going to assume water is available. So we remove that constraint, we remove that source of uncertainty, and we deal with evaporative demand. Okay, so this is basically taken in an equation form. The theta there, the theta is moisture availability. Basically, we wrap the rest of those variables up, and we close evaporative demand, and we say that ET is a function of water availability and evaporative demand. And then, if you want to get ET, we parameterize the water availability somehow from maybe a Landsat model, and we stick our evaporative demand into it, and then we get actual ET. Okay, don't worry about that. So once again, ET is the actual flux that we're always interested in. Evaporative demand is the ideal flux given a surface of unlimited moisture, and I prefer to use the word evaporative demand. So ET is supply, evaporative demand is demand, of course. And there are different strains of evaporative demand. There's PET, or EP, which is potential evaporation, which is Penman's original 1948 concept. There's a reference ET, which is encoded in the FAO56 and the ASCE reference, standardized reference ET. And then there's pan evaporation, which is the oldest measure, which is an observation. Okay, so there's two different ways of generally modeling these potential evaporation and reference EP. Using physically based model, which is always will be based on Penman originally, with a whole suite of variables of all the physical drivers that drive evaporative demand, or the temperature base, which you'll see here I've called T-base, which is generally a function of air temperature and some mishmash of latitude, day of year, diurnal temperature range, but very few drivers. And of course, then there's the pan evaporation observations that actually is a physical integration of all those drivers. Okay, so let's compare these modeling philosophies, the physically based and the evaporative and temperature based. So physically based generally is a weighted combination of a radiator driver and the effective driver. This is called the Penman equation, 1948. It takes those two drivers that I was talking about earlier, the radiator and meteorologic, and weights them together and then drives the equation. The temperature-based then, a Hargreaves reference DT equation, is just a function of maximum minimum temperature, the radiation of the atmosphere, which is that mishmash I was talking about, of latitude and day of year, and some empirical variables. How do they work? Oh, okay, so I'm going to get to maths here. So this is just a summary of what I've just been trying to say. Conceptually, they're different in the physically based takes both of the drivers and explicitly models them, where it's temperature-based. It says, the hell with the vector drivers, we don't care. Let's just look at the temperature and say that it's a proxy for the radiation drivers. Of course, the physically based are much more physically sound, and they match the observation as well. The temperature-based are convenient, and that's why very low data requirements. And the drawbacks are just the obverse of the advantages, of course. The data requirements are strict in the physically based, and of course each data stream brings uncertainties. And there's lots of varieties. The physically based varieties are generally based on Penman, and there's just a slew of empirical relationships on the right-hand side for temperature methodologies. Okay, I'm going to skip this. This is just a map of two examples for the same day in the Colorado Basin. On the left is a physically based Penman-Monteith reference ET. On the right is a the Heyman potential ET. And you can see the two equations. One's super simple, just a question of temperature, and one has all the drivers encoded. And they don't really look alike. They're sure that they're both higher in the southwest. Heyman, for example, the zero's out at 0 degrees, at 0 Celsius. The spatial variabilities don't match very well. There's almost no elevational trend in the Heyman EP there. I'm trying to set up a conflict between the physically based and the temperature based reference ET. This then is a physically based potential ET, pan evaporation, synthetic pan evaporation that I've derived using this Penn-Pan equation from the NL-DAS drivers. And I should just have a sidebar here and say that I have all these physically based potential ET surfaces for Penn-Pan, Penman, Penman-Monteith on a daily basis from 1979 to the present, if you want them. And they're at 1/8 of a degree.
You might want to say what NL-DAS is.
Say that again?
NL-DAS?
NL-DAS is a North American Land Data Simulation System. There is a driver, it's a reanalysis driver of drivers that put together on an hourly basis by NSET, which is an arm of NOAA. And I download those on a daily basis and run them off on a Q method.
Hourly radiation, hourly.
The drivers, yeah.
You went so fast.
I'm trying to squeeze it all in 15 minutes.
Squeeze it in, but it's, I think.
So yeah, the temperature, the specific humidity, downwell and shortwave, downwell and longwave, atmospheric pressure, and wind speed. Don't forget wind speed. Okay, so I'm trying to show here what actually drives the variability of evaporative demand across CONUS. And we're going to see how all those different variables play out in combination. So basically, this is looking at the variability, the standard deviation through time of annual pan on the center graph, and then January pan down here, and July pan down here, just to show that it's a dynamic process. It changes across the landscape as you shrink down your time frame, expand out the annual. Okay, so basically, I've conducted a variability analysis on this Penn-Pan, which is very close to Penman potential ET. And you basically, this looks like a complicated equation, but it's not. Just a bunch of components in different combinations.
And a miracle occurs.
No, it's basically looking at the sensitivity of Penn-Pan to each of the drivers, which is in analytical expressions, and then these expressions here then are just the variance of that driver, and then these are the covariants, for example, long wave and temperature. So we can derive all these either analytically or from looking at the data, and then we can combine them in these lines. And each one of these lines of this equation encodes the combination from one of the 6 drivers, temperature, specific humidity, yada, yada, yada. And they all add up to create the variability in pan evaporation. So we're just decomposing that variability and asking which driver is more important. And that doesn't matter. So this is the after the miracle we have the answer. This is the power of the driver in terms of percentage. What percentage is? It's almost like an R squared, if you like. What percentage of the variability in pan evaporation is provided by air temperature, and then by downward long wave. And of course, up here in your prairie potholes area, 90% of it comes from temperature. So your first answer is, oh, we'll just do temperature. That's fine. That's beautiful. But this is on an annual basis. You can see that these other drivers, atmospheric pressure is really irrelevant. You really don't need to model atmospheric pressure if you're going to do atmospheric demand. Downwelling shortwave also not very important. So you can cut out 2 of the drivers immediately and just focus on the 4 drivers that remain, which is what I've done in the next model of. This then is just the rank of each driver in space on an annual basis. And you'll see that temperature just dominates almost everywhere except for Florida and then far southwest, where specific humidity is very important, or downwelling shortwave radiation is very important. Okay, and this is summarizing that on an annual basis. What is the top driver on an annual basis? And the colors are really poor here. This is specific humidity here, shortwave here, temperature everywhere else on an annual basis. But let's look at this on a monthly basis, get a much more interesting picture. Dominant driver. I know somebody here, I think, was working in the Four Corners area, I believe.
Where?
Right.
There's a project there.
So in July, which is in the summer months for that area, the wind speed becomes crucial. Wind speed and specific humidity, that effective driver becomes the most important driver for variability in the summer, which is when you're getting most evaporative demand. Similarly in the fall, when specific humidity is important, or if you're working in the southeast, you've got to use shortwave, downwelling shortwave. So using a temperature-based approach in those areas, you're losing the picture. Okay, then I'm switching models here, and now I'm using a model of reference ET, using a very similar model, but only has these 4 parameters, the 4 that I said were important before. And now I'm looking at a daily reference ET, and I pull them all into months. So you can see the months going across, and this is the dominant driver of variability of daily variability pulled into those months. And then you see, in the summer you see this bloom in the west of wind speed. In the east, southeast, you see shortwave radiation is more important. In the winter, then you see in the Atlantic states, it's specific humidity. So it's a much more complicated picture as you change your time frame. And I don't know, if you're looking at your climate models projecting out into the future, then maybe temperature, maybe you're only looking at annual data. I don't know, but you certainly don't seem to be. You're looking at more monthly or seasonal data. This then is it's the same approach, it's the same 4 variables. I've pulled it across the entire May through October season, and you can see, clearly here again, the growing season, temperature is not that important. The warmer colors indicate the most important. That wind speed, again, is the most important here. And that's the annual picture for this model annually. And it's a much more simpler picture. Then this is what drives annual variability. Once again, it's a much more simple picture. The last slide was daily. This is annual. I'm modeling on an annual basis using annual drivers. And temperatures almost everywhere except for some of these southern tiers of the United States. So it's a very dynamic picture depending on time frame and depending on landscape, on space. Okay, so that was spatial variability. Now moving on to trends. We're trying to stress the importance of not using temperature-based parameterizations of evaporative demand in trend analyses. We know that evaporative demand is generally decreasing worldwide. All these people have said it in all these regions. Oh, this is a pretty good summary paper, this geography compass paper, if you want to look at that. It summarizes all these various studies. This is work I did here for my dissertation, was just looking at pan evaporation trends across CONUS. See annual trend, 64% of the pounds are decreasing, and warm season trend, 60%. So about 2/3 of the pounds are declining, indicating that the last 50 years, the recent 50-year period, that evaporative demand is actually declining, which is in opposition to what you see from projections of evaporative demand from climate models. It all show it increasing.
What you mean is the climate model simulations of that same period all show it increasing, right?
I think that's what I mean.
Yes.
But you know what? I don't do enough climate modeling to be totally confident to answer that question. I don't do any climate modeling.
Right.
So that's a very good question. I think we should.
As well as the future projections, but you're saying even during the past, even when the models are used to simulate the same period, I think you're finding a difference, if I'm right.
I am not finding a difference.
They are.
I'm not doing that work, but you're probably right.
Yeah, I have to go double check that out.
Okay, so this is some work we did in Australia, decomposing, once again, instead of the spatial availability, we're decomposing the trends, what's driving the trends of evaporative demand. And for evaporative demand, we're looking at pan observations. Remember I said they were physically integrating all the variables, so it's the best measure we have. So you see a negative are the dark circles, positive trends are the light circles. So spatial average of 2 millimeters per year decline in pan evaporation. So we decompose that into a radiative component and an advective component. Together they sum to the total. And we see that the radiative component is actually driving pan evaporation upwards, but the advective component is driving it much stronger, more negatively, almost minus 3. So we further decompose this advective component, and to our surprise, so now we're looking at only the advective component, decomposing it into a vapor pressure deficit component and the wind speed component. It's all wind speed. It's been driving the evaporative demand trends in Australia. This is Australia, this isn't Cones, but it's very interesting to find that wind speed is driving the entire trend in pan evaporation. And I don't know if I have a slide. No, I don't have a slide that says this. The big story is that wind speeds are declining worldwide, almost in parallel with pan evaporation. So it's very interesting that the single driver that's driving these trends is declining almost globally on land surface. So if we don't capture wind speed trends, we're missing the picture. Okay, so this is, I looked at the PDSI back in 2008, and the PDSI at that point is only driven by temperature-based methods, so it's almost a form-based approach. So what I did here is I looked at the temperature-based driver of PDSI, and I output the trends in potential ET, actual ET, and soil moisture, and then did the same thing driving the PDSI with pan observations, which is the physical drivers. And you'll see that the PET, or evaporative demand trends, are radically different. Of course, they're all positive in the temperature-based method because the temperature is rising. When you actually use a real observation of pan evaporation, you get very different results. We have declining PET trends. Driving that through the PDSI model and actually outputting the actual ET data sets, they're not so different in Australia, but in water limited Australia, but in energy limited New Zealand, it's a change in sign, simply by changing the evaporative demand driver. And soil moisture, we get similar results, very different soil moisture trends. When you plot the two trends from the two drivers together, there's no relationship between them. Okay, so this is a sensitivity analysis I did of running that data. This is a bit of a complicated graph, to apologize. So here what I'm doing is I'm comparing the physically based evaporative demand drivers to the temperature-based evaporative demand drivers. And here I'm holding precip, I'm only letting precip vary, and here I'm only letting evaporative demand vary. And according to the hydroclimate, you get different results. The bracketed numbers are the slopes of the response. So in the energy limited areas, that is New Zealand, your choice of evaporative demand is crucial. Where are we? So like here, the slope of this response is twice the slope of the temperature-based response is twice the slope of the physically based response. So it's very important to make the right choice of evaporative demand driver in energy limited areas. In water limited areas, that is the Australian population, it's not so important. They're very these slopes, that is with just looking at PET forcing, are much smaller than these slopes, which is just looking at precip forcing, regardless of which one of these drivers you choose. So your choice in water limited areas isn't as important as your precip force, which makes perfect sense to us because the hydroclimate is much more responsive to precip. Okay, so this is the summary of the recent Nature paper by Sheffield, Roderick, and Wood. They repeated the same sort of study, but did it globally using a beautiful data set. Ran the PDSI with temperature-based and physically-based, or Penman-Monteith-based evaporative demand driver. And here are the temperature-based results, and here are the physically-based results, and this is the difference between the two. And so the E0 trends, that's the evaporative demand trends, in the temperature-based, 98% of the land area shows an increasing evaporative demand trend. That's the temperature-based trend. Physically-based, it's only 58% of the land area shows increasing. The PDSI trends, the increase in area, the area of increasing PDSI, that is increasing drowsiness, is 7 times as high as the area when you use a physically based evaporative driver. So they conclude that there's very little change in drowsiness over the past 60 years when you use a physically based driver. There's different demand trends with various driving that. I'm just going to skip through this. So that was, we looked at spatial variability, we looked at observed trends. How do we move forward in time modeling? I mean, as far as I can see, there's 2 approaches. One of which conserves parameter parsimony. We look at temperature, we look at latitude and day of year. Each of these has a little cloud of uncertainty that's associated with it, like the data uncertainty, the modeling uncertainty when you drive the radiated model, latitude and day of year to drive a shortwave. The modeling uncertainty and temperature-based modeling, and of course you have uncertainty with your output for your climate prediction. On the other side, then we have a bunch of uncertainties from each of the data sources. We don't have much uncertainty in the physical model, but of course then we have uncertainties here. So how do these 2 uncertainties compare? Well, I think that's a fascinating study that we haven't done really. I think that's the question that you really need to. I think that's the question you're really asking fundamentally. Sorry about the cartoon.
Say that again. What do you think the fundamental question is?
Well, do we want to just conserve parameters and reduce our uncertainty in our variables because we're reducing the variables, the number of variables, or do we want to increase and use a crappy model, or do we want to use the best model we have and accept that each of the data streams, of the 4 now data streams or more, has an associated uncertainty. And I think we're all biased toward this side, but how do we do wind speed projections? I mean, it's hard. Right?
And this is also really an issue if you want to extend your analysis back, say, to the early part of the 20th century, using, for example, the co-op meteorological stations we have, T-min, T-max, and T-tip. And so there are some fairly good observational data sets that have those variables, maximum temperature, and nothing else. You have to get, if you wanted to use this method, you're going to have to, I mean, there are ways you can get estimates of those, but they're much cruder estimates of those other fields. So that motivates the use of a good model, building better models, and people are. Right. People have built reasonably okay models of that, I think.
In fact, as an interim approach, David King, I think some of you probably worked with him, and Amy Substan, maybe not.
Dominique Bachelet and
they've just submitted a paper where they take like a middle approach, where they take temperature, relative humidity, and shortwave radiation and ignore wind speed and drive this physically based model and get pretty good results of matching the current climate. But I just wanted to talk a little bit about a drought index.
Well, 25 minutes.
Oh,
we actually
okay.
went 10 minutes over.
All right. My first interest of, this was Charlotte's slide. And so the take-home message, forget about this. This is a take-home message. Many people don't know if they're using a temperature-based parameterization factor. It was a surprise to some very top scientists when they were running their PDSI trends. Check if you can do so. Check if you are, and if you can avoid doing so, do.
Okay. We'll have the PDFs of these available if that's okay.
I have to come back to
Okay.
I'll do that. Yeah.
But we'll have the presentations available. I think that Kyle, we're waiting to get the capacity to show his slides, and I think Bill, not here or on the phone, so we can just go maybe to Gabriel talk. That might have saved us 20 minutes right there. But we'll show Kyle, but let's move forward to
good.
Yeah.
Gabriel's.
Okay.
I'm popping the agenda a little bit out here as to.
Okay, sure.
And I'll just hand it over to Gabriel.
Sounds good. All right, thanks, Jim.
All right. So I think Mike, he gave a very good overview of what, the potentiality that break demand. I'm going to use that in the estimation of actuality using satellite data. Where's my PowerPoint? Why don't I go to my PowerPoint?
Actually, get the arrow now.
Okay.
So there we go. Good, thanks. Arrow.
All right. All right, just in terms of time, so there will be a summary and focus on modus-based ET and Landsat conclusions. All right, so nobody's in a hurry to leave the room, but if you're in a hurry to leave, the message in here is that if you are interested in running ET actuality, use land surface temperature derived from a satellite. And for application for drought monitoring at scale, like 1 kilometer by 1 kilometer, I'm going to show you examples. It's good as is. If you want to use that for water balance studies where volume metric amount is important, then there's a bias correction you have to apply. Right, so it's part of the hydrologic cycle. We're going to focus on evapotranspiration. Some people separate the evaporation and the transpiration that goes through the plant roots, and the estimation I'm going to show is a combined, so evaporation plus transpiration together, ET, evapotranspiration. There's a history, was funded by different USGS groundwater program, and for international applications, now the Water Smart, this stands for Managing America's Resource for Tomorrow, and USGS water census. The first funding came in for groundwater availability in the Northwest. The idea was, can we estimate, the amount of evapotranspiration in this basin? And precipitation, blue is much higher precipitation, and then this is satellite-derived actual evapotranspiration, so green is higher ET. So at the annual scale, we just do a difference, and you get a water balance. You see in here, red is negative balance, which means the evapotranspiration is much higher than the precipitation. So where is the water coming from? So obviously it's from irrigation. Where? Is it from groundwater, from surface water? Then that requires further studies. But these are also the supply regions where streams generate, and this is the sink area. If you look at that precipitation and ET on a monthly time scale, this is an irrigation basin in Yakima, and you can see almost every month the ET is much more than the precipitation, so the difference must have been made by irrigation. So at Water Smart Water Census, what we do is just improve the ET model so that it could be applied regionally and nationally for estimating water use, how much water is being used, and for water availability. The two scales we are talking about is the water use, so we want to know who is using the water, so it's really at the field scale, so the Landsat about 100 meter by 100 meter resolution. And if you're not interested in who is using the water, just we want to know at the basin just how much water is being evaporated and how much precipitation comes in, how much gets lost at ET, and then discharge. Then modest kind of scale is enough, 1 kilometer. 1 kilometer versus 100 meters. Landsat versus modest. So what is the role of remote sensing estimating evapotranspiration? Well, remote sensing is a data source, so we get data to run the different models. You run energy balance models. I'm going to talk a little bit later. So the land surface temperature is the most important. Again, if you run Landsat, you get 100 meter resolution. MODIS, ADHR, 1 kilometer. And these are geostationary satellites, you could get a 10 kilometers. But if you run a water balance model, then precipitation is your main driver. From NEXRAD, it's available daily, 5 kilometer resolution, satellite base for the world. From NASA, 25 kilometer, and from next. All right, so the two principles of really estimating actuality, that's the water balance, so which is really an accounting of precipitation, and energy balance is really from land surface temperature. I was surprised, I was happy to see this quote as well in this room. So yeah, this is one of my favorite quotes. Next. There are so many models, so if you go in the literature. So people, I think, choose models because that meets their objectives, so they can apply, they can implement themselves. So for us, we use what we call a VGT model, and from surface energy balance model, in the literature, we developed something what we call evap. Next. So water balance model, it's a simplified schematics of the water balance model. The starting point is the potentiality that the evaporative demand that Mike talked about, but that's when water is not limiting, right? So if water is limiting, then you got to have a correction coefficient for example, hydrology, soil moisture. Then how do you do that? You do a simple bucket model, for example, in a one-dimensional. The input would be the driver would be the precipitation, and then you got a bucket depending on the clay soil, sandy soil. For that you can get information from StatsGo. And you do a basic daily soil water counting, and this coefficient could vary from 0 to 1. If the bucket is 0, this coefficient will be 0. If the bucket is full, this coefficient will be 1. So which means, this would be a 1, then the atmospheric demand or actuality is the same as potentiality. But also, it varies by crop water use. Then you'll get an idea of a water use phenology, for example, from NDVI. That varies. So at the growing season, the water extraction is much higher than during the winter season. So if you apply this water balance model daily, this is an operational that we post in the U.S. on the website at 7 p.m. This is as of April 28. You can see much of the West and Texas, it's kind of in a wilting point. So the bucket is very low. It's driven by the daily extract data. Whereas in the West and the East, kind of moisture is abundant. Next. So this is another day. So if you can do this really daily. This is I think at 5 kilometers we run it, but we can run it at 1 kilometer as well. Next. This is I think an illustrative example of the difference between potentiality and actuality. And this is what you see in the green line is atmospheric demand from GDAS, Global Land Data Simulation System using the Feynman-Montes equation. So what you see in here is the actuality, and the one in here is the rainfall. So it's really, if you look at it, when the rains are limited, the atmospheric demand is much higher. But because the rains are not there, the actuality is much lower. So it's really limited by soil moisture. Now, rainy season, rain, and because of clouds and stuff, the potentiality is actually lower, the green line. But it matches now with actuality. So that's really the difference between the potentiality and actuality. So the actuality is, okay, depends on the potentiality, but also it depends on soil moisture, which is the rainfall. So the kind of model I showed you requires good rainfall data. You need to know this. You need to get good information on soil. So that's not really a problem in the U.S. But it's very difficult, and this is very important. With that kind of model, we don't know the irrigation application. So we don't know how much farmers are applying in the land. The amount of water being extracted by deep-rooted plants. That information is not, if it's not in there, it's not in the model, so you cannot get a good estimate. And also the impact of pests and disease is not included in our model. Next. So we have developed an energy balance model, which is the land surface temperature tends to incorporate all of that information in the system. Thanks. This is a schematic of the model. Again, the starting point is the potentiality. If water is not limited, this is what Mike showed. And then we use the land surface temperature to come up with an 80 fraction, takes into account the hydrology and the pests and diseases and other stresses, so that varies from 0 to 1. Land surface temperature, when it's a well-watered plant, is much colder than a dry, bare soil. Difference between this and this temperature could be as high as 20 degrees centigrade. That's really the main driver for the hydrology. Without going through the equation, what we are saying is we can derive ET, actual ET, from the potentiality, Feynman-Montes, and then getting land surface temperature from a satellite. All these other parameters are derived from clear sky radiation. So it's really the land surface temperature is this parameter, but we need a Feynman-Montes equation for the atmospheric demand. This is the last schematic of the model. If I can explain this, I think it's more than 50% of the model. This is how it works. So let's say on July 4th, one day, this is from modest land surface temperature transect, New Mexico to Oklahoma. What you see in here is elevation differences. So this is the land surface temperature varying, from west to east. So let's look at 2 points in here. So this and this, they have the same land surface temperature, but for a different reason. This one is in the forested area, probably a wetter environment. This one is in a higher mountain, but much drier condition. So if you just look at the land surface temperature by itself, you could get confused because it doesn't really tell you much. But you have to put it in a boundary condition. So this one is assumed the air temperature, and this is an assumed dry condition. So if you plot it in relation to air temperature, it's much closer to a dry condition, or it's away from the air temperature. So it's much warmer than air temperature. Whereas this land surface temperature is much closer than air temperature, which means there is a lot more latent heat flux, and here there is a lot more, much higher sensible heat flux. So that's really the main driver for the whole model. Next. So I mentioned about air temperature. We get air temperature in the U.S. from DAMET and PRISM for the world application, world climate. This is what I said earlier, and this is what Penman is from Mike and other groups. But if you're familiar with this, this is like a MODIS sensor, and these are the different parameters. So the most important information is that we get daily data of land surface temperature, actually twice a day from MODIS, and Landsat every 16 days for the land surface temperature. MODIS got 36 bands. The land surface temperature comes in one of these bands, around 10 micrometers. An example of land surface temperature freely available is an 8-day average. It just looks like this, so anybody can use this data. And the Penman-Montes equation solution we solve this daily, same equation Mike showed. We use this just for water unlimited conditions. An illustrative example of how this works, okay, this is pretty much a cold boundary condition, kind of the air temperature, and this is our land surface temperature. And what you see in here is we convert this into ET fraction, then actual ET, and this is a comparison with flux tower. So so there is very good comparison. Next. And this is another site in Oklahoma. Again, this is MODIS versus flux towers. So we kind of build confidence. Next. Now we compare it to other models. Some of you might be familiar with the MOD 16 data. This is a NASA official product. This is annual total I'm showing you. This is a gridded flux data from Max Planck Institute from Germany. And this is a water balance ET, which means annual precipitation minus discharge from USGS. So at the HAC basin, HAC scale, HAC 8. But generally you can see higher ET nowadays when there is rainfall and vegetation. But you can see with the land surface temperature, there's more details, like the Central Valley and the Snake River Basin. So the land surface temperature gives you a lot more details, especially in irrigated areas and wetlands. Next. This data is actually now available on the GeoPortal from USGS. Next. So I'll show you just applications and drought monitoring and stuff. Next. So this is now SAID looked at this product and said, can you do this globally? So what I'm showing you is the anomalies for available. So this is 2013. You can see the drought, and still there was in the high plains in California. So I was surprised to see also drought in Brazil. So these are just, this is the average condition. Next. Yeah, please. So, I think we missed one. Can you go back? That was 12, one more? Okay, yeah. So I'm just going to show you 2 years. So this is 2013. You can see the much higher extent of drought in 2012. As you can see, it's not only in the U.S., but also in Europe and Russia, and again. So just the point is you can do this globally. Data is available freely.
Can you say what this?
Okay. All right.
A little bit. This is a drought monitor. This is a drought measure.
Yeah. So what this shows here is, so we calculated ET, seasonal ET, for the time period from, in this case, if you could go back and then the previous one. Here, so it's a whole year. Oh, so let's say from March to October. So March to October, this is seasonal ET total, and we compare that to the 10-year average. So this is a percentage in the 10 years period. This is below that 10 years, the total ET. So it's seasonal ET. So if the seasonal ET is lower, which means the drought condition, the seasonal ET is much higher, it's a wetter condition. So this shows you, for example, compared to those 2013, years, we've got a lesser ET because of lesser moisture. or it could be a combination of moisture and energy, but most likely it's limitation of moisture.
So you're using actual ET as a measure of drought.
Right. Oh, absolutely.
Okay.
Actually, I would argue that actual ET is more powerful. But yes, potential ET has got a lot of value. I think we had the discussion with Mike, and maybe there's an indication of early onset of drought and stuff. But the actual ET should be the one you should look at, because that's the one that tells you how much your vegetation is evapotranspiring.
Yeah, I'm just trying to compare this to like a PDSI, which kind of does that, but through a simple water balance.
Yeah, definitely.
Or the SPEI, which does it implicitly by P minus PET. Well, if you have enough. But
it should, no, I think they should all talk in the same way, because in the P minus, ET, is also there is a supply and there is a demand.
Under certain conditions,
this also includes this pretty much whether the demand is being met. This is how much
Yeah, this is like the ground truth. This is what really is happening on the ground, and this is the anomaly from what really is happening on the ground. This is like the perfect signal for drought almost.
Well, except you have to know what is drought and what is just normal variability, right?
This is compared to those 9 years of data.
80% of average may be just fine, but 60% of average may be.
Right, and then you have to compare to yield data, crop data, and stuff like that, and to see really the impact on socioeconomics. And
because the PDSI has the SPEI is a standardized index. Whereas this isn't necessarily standardized.
We can also standardize this, in different.
I'm just trying to understand the differences, because we might want to build something out of climate model data, and understanding that why not just use the evapotranspiration from the climate model? Why not? It's just one field.
Potential ET or actual ET?
Actual ET.
Yeah, definitely.
As a measure of droughtiness, why do we have to go through? Anyway, we can discuss that during the discussion period. But.
So this is a more recent, now this is a close-up view. Again, this is actual ET. These are seasonal ET estimates of really amount of water that will evapotranspire. But, it's a color saturated, so you don't see. I'm going to show you next one, anomalies, next. So what I showed you earlier is really, the percentage of the average year for that time period. So you can see really the drought years show up. If you remember, some of your regions, shows up in 2012, 2013, California, and Central. This is more recent. So this is 8 days. This is updated every 8 days. This is from April to this month. It shows much drier condition in this region. The comparison with the drought monitor is also. So this is automatically generated. Like the data comes out, computer processes, just the graphics is posted. This requires a lot of people looking at stream flow data and other rainfall and stuff. Again, similarly, previous years drought monitor, and this is a weekly product. This is a seasonal product. So if there are differences in space, that's because they represent different time scales. I just want to show the high resolution scales with the Landsat. So we use the same model now being applied on Landsat, 100-meter resolution versus a 1-kilometer model scale. At this scale, they look very similar. I'm going to show you a close-up though. This is Landsat, just background image. This is vegetation irrigated field. This model, you can see the pixels. Each one of them is 1 kilometer. Next. So you can see the Landsat just much higher definition because of that spatial resolution. So next. Base map, MODIS, really an average of all this, and Landsat. Again, just same model, similar principles. Again, MODIS and Landsat. So really, if you are interested in water rights in farmers and fields, so Landsat is the way to go. You can see the center pivot. So this is really amount of water, seasonal water being estimated, being pumped or used by the crops, and this is from MODIS. Now we've been asked to do similarly in other basins. This is in the southeast of Flint, KCF, Apalachicola, Chattahoochee, some of you familiar. So this is an ET estimate, and this is a land cover map of that region at 100-meter resolution again. So what we found out actually crop areas are much more ET than natural vegetation, because natural vegetation is extracting water throughout the year, whereas crops are only extracting during the crop growing season. So kind of a different, first we didn't expect that, but that's what we found, and that makes sense. This is in Delaware Basin again, similar kind of distribution of ET. The cropland is much lower than the woodlands and open water. And you can see, the forested areas and the ridges and have higher ET than the croplands. Next. Just a close-up of, again, at the HAC level, looking at hydrology groups and center pivots. Next. Urbanized areas, of course, higher land surface temperature, as you would expect, lower ET, whereas forested areas will have a higher ET from the areas. This is a validation with lysimeter data. In the interest of time, I'm going to just pass, but just there is good validation with lysimeter data. Next. Now, there was a challenge whether we can do golf courses. Next. This is a base map. Next. And this is the ET. So really, the golf course showed up. There was a very good contrast. This is in the Phoenix area. We didn't do the research yet, but we want to separate also public versus private, or one is watering more, using water. So basically, we can really, satellite-based ET estimation is ready for a lot of applications for irrigation, water balance studies, and drought monitoring. So people I work with, graphics I didn't generate, but they help. Yeah, that's all I have, so we'll be happy to answer any questions.
Pretty stunning, that landscape.
Yeah.
So I think we've got Ben Aligna from CU Boulder, sits at NOAA on the line.
Yes.
Okay,
can you hear me over there?
Over to you, but in the meantime, if there's any questions for Gabriel, we'll take those now. It's really pretty interesting. And I think that, it reminds me of vegetation, using vegetation for MODIS or Landsat for a habitat model, but then how do you project? How do you go into the future? It's a similar issue here. You got Landsat, you guys could probably do some pretty neat maps, but then what do you do? So that's just sort of maybe table for discussion, and kind of the main part of this, I think, workshop is then to say, okay, so what do you do when you go from the current, or establishing relationships to projections into the future? So interesting stuff.
And I can ask you the same question I asked you in the email, but in front of the audience. And you talked a lot about croplands, but you showed maps for wild, natural landscapes. And so my question to you on email was, how well does it do on natural landscapes, and is it really applicable to something like a stage step or something like the grasslands up in natural grassland?
I think that's the advantage, especially land surface temperature. Very little you need to assume. So with the water balance approach, there's a lot of models you need to assume how optimum and how the water supply with the vegetation is healthy and naturally. Land surface temperature is supposed to include all that information. So we're very confident, actually, that it applies anywhere.
Once you have a good estimate of evaporative demand.
Right. Assuming that evaporative demand is handled by Mike, so he gives me a good, atmospheric demand. So the land surface temperature is supposed to capture really the stress that's caused by mainly moisture, but also other stress like salinity and pests and diseases should be incorporated in land surface temperature. Like you stick a thermometer to find out if the overall health of a person is. That's really how I see it. Whether you stress your body and you are not, using water properly, so your temperature rises. The same thing with the land surface temperature. It's not losing, it's not doing evaporative cooling. It gets stressed. That shows an increased land surface temperature.
In areas of open water.
Open water, it's really very tricky. The open water, I think it's very questionable. We have to be very careful in how we analyze this in open water because, water is not limiting, but the depth of the water will have a different energy balance scenario. So I think Helen also, I was going to ask her earlier, when you apply the Penman-Montes reference ET over open water, I think that applies, the area around open water. But depending on the depth of the water, the amount of ET you get will be different. If it's a deep water, there is a lot of the radiation goes deeper into the system, so it doesn't really contribute to the evaporative layer that's as a top layer. If it's a shallow one, but there is a lot more energy available, that it heats up the pool and it contributes to the ET. So we really have to look at the pond size and the ET we get out of it. So it's just not because it's open water, whether it's a deeper pool or a shallower pool, that will be a difference. So energy balance of the land surface at present is different from energy balance of a water body. But that's an important distinction.
Cool. Right. So, Ben, we're not seeing a clear picture of your desktop. It's sort of pixelated, strange coming through. I don't know if you shared the desktop.
Oh, yeah, I have. Can you hear me over there?
Yeah.
Oh, okay. So, yeah, I've got it sharing, and then there are some options here. Maybe I can manage the full screen. Did that improve it?
No. Another option would be to send me slides.
Okay.
I can show them.
Okay. Let me just try one more thing. Here. Oh, maybe this will do it.
Promising.
Did that?
Oh, it looks green, at least instead of funny.
Oh, WebEx just quit. Okay, so that. Okay, so yeah, let me send you the slides, and that should probably.
I'll watch for those.
Okay.
Well, while they're doing that, Helen, did you want to lead a little discussion on what we've seen so far?
I think the ecologists could probably use like an actual ET versus potential ET distillation. Speaking for myself, I don't know. That I think I guess like I'm not totally clear on what the best measure of drought is. I mean, my sense is that actual ET, what I thought was that it mirrors precipitation just like what you were showing. So it sort of integrates all of that already. But then it kind of gets to what Jeff said, like how do you use that, especially in the future. So I'm not.
I imagine it would depend on. You're trying to get an indicator, sort of regionally, of pond count. So, and you're using a statistical relationship for that. So I'm not sure it. Matters as much, but some models use PET as potential evapotranspiration or evaporative demand as a kind of stress on the plants themselves, as I understand it. So I would imagine the conceptual way in which you're using these in the let's just call it ecological response models or habitat response models as this is no one answer. It depends on how you conceptualize.
So, but if you were to plot actual ET against precip, and given that most of the north central region is pretty dry, would that, how much information does it add, or does it add information seasonally, but not sort of at a coarser time scale? Is that the idea?
Well, I mean, there's going to be a strong relationship between, precip and ET and rainfed systems. The difference will come in like in wetland areas, where the water comes in from other areas and accumulate. And then the actual ET will show you much higher ET and, ecosystem, taking advantage of that. Maybe there is no precipitation in that wetland area. Actually, the water is coming from somewhere else. So that information would be captured by the actual ET, but not by precip.
Okay. So it's actually AED, is it a response of itself? I was under the impression that it capture potential evapotranspiration, actual evapotranspiration, plants in that area actually kick off. Is that wrong?
No, I don't think that's wrong. So yeah, the maximum amount of actual ET will depend on the potential ET. So really the potential ET is the maximum boundary. The actual ET is really what happens that went through the plant system.
So it's a response.
It's a response.
So if we were going to planetary layer and species distribution model, we'd almost be double stacking. And it might be better to focus on a PET product, for instance, or a soil water potential product as an explanatory. If we're trying to characterize, say, the suitability of a plant in a given area, given some function of drought. Is AET, has anyone used AET in an SDM as an explanatory? That's kind of what I'm hinting at. It doesn't work.
SDM?
Yeah, species distribution model.
Thank you.
Like a GLM, a correlative model that makes a decision on whether or not a place is suitable for a species.
So how do you account for like a wetland area where the water comes from some regional groundwater flow, but the PET is, let's say, very low generally?
Yeah, the PET probably wouldn't capture that.
Yeah.
I would say use a mechanistic model that.
Yeah, then you depend on how well that mechanism model captures that mechanism.
But Helen's approach is going to be using sort of a regional drought index as an index of that kind of regional hydrology, hoping that it's fast enough.
Right. Move on to Ben's talk. I think this is the kind of thing we'll talk about in the last 45 minutes of the meeting, the question, and then beyond that. So Ben, hopefully you can see your slides, and I can move through them as you talk.
Great. Okay, yeah, thanks everyone, and it's a real pleasure to have been invited to speak, and I apologize that I could not be there in person. However, I hope to add to the discussion, and I think my small number of slides will help us keep on schedule, so hopefully that's a good thing. Okay, so my background is primarily, we can move on to the overview here. My background is primarily in land surface modeling and multi-scale hydrology. So I'm just going to give a very basic overview today of some of the issues related to ET for running those types of models. I think Gabriel and Mike have both done a really nice job laying out some of the important ideas. Okay, so I'll just start with, what is ET, how is it modeled, why use land surface models to predict ET, when they might be better or worse, and I'll briefly look at how models compare to each other and discuss how they may compare to remote sensing. Okay, so slide 3, we've definitely covered a lot of this. Basically, we know that ET describes, the sum of two terms, and it's I think of it in terms of, a way of partitioning precipitation between runoff and soil moisture, and also how much re-enters the atmosphere. And in a way, ET represents a dynamic equilibrium at the surface water balance. And from my perspective, it can be really important for, of course, hydrologic forecasting and when we couple and working with numerical weather prediction models. Okay, so slide 4, how is ET modeled? So it's in these hydrology and land surface models, it's common to use, as we've heard, the concept of PET, essentially an environmental demand for ET. And some of these models actually, like the VIC model, for example, actually dynamically compute PET at every time interval. So that could be, hourly or, 3 hourly or daily. And that's a function of net radiation, which is estimated by algorithms, which I'm not going to actually talk too much about today. For example, the MT climb algorithm that Joe is, I think, mentioned earlier. And a function of wind speed, which is a forcing variable. And so one of the useful things for us to sort of categorize the land surface is look at places where, ET is close to potential evapotranspiration versus areas where it isn't, and we can glean a lot of important information there if we're sort of water limited versus energy limited. So if we switch to the next slide here, slide 5, just kind of a little bit more detail here. So oftentimes in models, some land surface models like CLM or NOAA or the VIC model, ET is actually partitioned into several subcomponents. Okay, so and you can kind of click through the animations here. So you've got, of course, when we exclude snow, you've got water that gets intercepted by vegetation is available for canopy evaporation. Then throughfall can become direct soil evaporation. And perhaps most relevant to the discussion today is transpiration. And this is sort of root water uptake that becomes water that emerges through stomata in the leaves of the plant. And so this, this last term, transpiration, is kind of, there's a whole range of ways that it's parameterized. But oftentimes, there are a set of terms that are used to govern sort of, or to define the resistance to ET or to transpiration in this case. Things like soil moisture stress or radiation or there's an optimal temperature range for transpiration to occur. So these models generally compute a PET, and then based on the conditions at the land surface, things like soil moisture availability and the other factors I mentioned, they will compute some reduced amount of actual ET as a function of those resistances. Does that make sense? Is everybody following? Okay, and so then, just to try to figure out, this is kind of more of an aside, but how much, what's the breakdown between these components globally? Well, that's very difficult to say, and sometimes these models get actually calibrated to try to assess the total ET, but oftentimes it's this breakdown that we don't have such a good handle on. So some work has been done. I'm quoting a few estimates here that based on global models that say, roughly about half of the total ET comes from transpiration, and then there's, perhaps slightly more soil evaporation versus canopy. And one of the issues here is that, the assumptions are that when you have a wet canopy, then your transpiration cannot occur. And so a lot of this is to do actually partially with the meteorological forcing. And I won't really go into that too much, but just to be aware that, there is, I guess, a very coarse consensus on, transpiration being the dominant term there. Okay, so the next slide here, I'm actually comparing a simple soil moisture accounting model, which is the Sacramento model, against a more sophisticated land surface model, the NOAA land surface model. So before I make that comparison, actually, let me just say, why do we use these models in the first place? And I think one of the reasons is we can actually get out of them some continuous simulations, and pardon the typo there. These can be daily, sub-daily, hourly. It really depends on how confident we are in our inputs. And the nice thing with these models is that they close the water and balance by construct, and in some cases the energy balance. So that means that, and I'll show a couple, I'll just show one graphic at the end, basically saying if we know what precipitation is, and we have some estimate of discharge, stream discharge, then we can pretty well constrain our ET to be the residual of those terms, at least on a long, over a long time scale. And then if we're comfortable with the way that the model is essentially partitioning the water budget, then we can perhaps apply it at shorter time scales to look at some finer detail things. And so what I'm trying to show here is that actually models can have greatly different estimates of PET. So in the Sacramento model, the PET, which is that blue area, and actually I scaled them according to the magnitude here. This is for the Sacramento river basin, actually in California. You can see that the Sacramento model has a much larger evaporative efficiency in this case, perhaps 1/3 of the PET, and I believe this was during the, I should actually label this clear, I believe this was during the summer months, whereas the NOAA land surface model, not only does it have a larger total PET, it has a smaller evaporative fraction, which is actually subdivided into separate components because it actually accounts for those components. And those are the soil evaporation, snow. I guess this is actually for the entire year here, because we have snow. And so what you can see is that actually you can have largely different model assumptions, but then the resulting total ET is actually similar in this case. So the next slide, I did a short intercomparison between several popular land surface models to compare the ET components. And I'm just going to show the total ET right now. If people would like, I have some extra slides at the end I could share. But basically, I just ran several well-known models, the VIC model, the NOAA land surface model, CLM, for 15 years, and I compared with the same meteorological forcing data, and I compared the seasonal ET components. And so, yeah, as you can see, a very coarse picture here. The total ET between the models has some important differences, and you can see in the north central sort of more easterly, there are some differences. But by and large, the total ET is similar despite these differences in modeling assumptions. And the reason for that is largely because these models have been calibrated to stream flow, so that if you believe the precipitation and then you calibrate the stream flow, you get somewhat consistent estimate of ET. Although what causes the differences are the assumptions in, for example, land cover and the mechanisms by which they compute ET. So there are still assumptions that the user will make that will determine whether or not a given model will produce, can produce different results. Or, of course, the choice of model can produce different results. So, finally, just to kind of discuss how models may compare with remote sensing. So, as I was saying, the models are generally calibrated to precipitation and discharge, which makes their ET on average very reliable. And so I'm showing this figure here of some basins that I had calibrated the VIC model, for example, to. And you can see, obviously, the north central is kind of contained almost entirely in the yellow Missouri River Basin. But what that means is you end up with precipitation as an input, Q being calibrated, which is discharge. So you end up with ET relatively reliably. And you can also do that over smaller basins if you click the animation of the next down arrow. And so remote sensing estimates, I think, my experience has been that they can provide very useful spatial information because they're observing, as Gabriel was showing, the skin temperature, which is, there's an incredible amount of information there. Although I have found that in some cases they're unconstrained by moisture availability, and so that's where we need to be a little bit careful, I think, when applying them, for any application. So that's basically it. As I showed, models simulate ET generally based on PET, which is either an input or it can be computed based on atmospheric demand, and of course assumptions about the land cover. So, and these can vary between models. And so we saw that on a coarse scale, ET between models is comparable, but differences do exist. And I think that comparisons with remote sensing require reconciling some of those constraints in terms of water availability, but can still provide very valuable information, I think, especially if we do that, if we apply these techniques in combination, so models and remote sensing. So thank you very much.
Yeah, thanks, Ben. I think that was a nice synthesis type of presentation already.
Yeah, and thanks. And I had some other slides, and depending on people. Oh yeah, so these are just extra slides at the end.
Could you flip back to your conclusion slide?
Yep.
Just leave it up there where we talk.
Well, I'm just trying to see where I'm just looking where we were with. Okay, so we're sort of Kyle. I'm going to try to get him started on this open office, but let me go to the conclusion just to leave that up while we do that. So I can do this.
So yes, any questions? Feel free to ask.
I don't know what I do next, Kyle. So I got open office. Okay. I'll handle it.
Log into the WebEx and just run from this machine.
Yeah, if you can do wireless there, that's sort of.
Oh wait, no, I was having trouble getting onto the wireless.
Oh, you were?
Yeah.
I think for mine, I'm going to do it that way too. I'm going to run from my.
Yeah, doing it on the wireless. That's probably.
Oh, more is that?
Okay, maybe I can show Ben's conclusions again while we're doing that. And I will watch for you to come online there.
Instruction, yeah. Sounds really done it here, but I think that's the best problem. He keeps having trouble getting open office.
Yeah.
I've got it now, but
Yeah. Is it working, or?
yeah.
I thought you were still having trouble getting it up there, but.
I just don't know. I've never used OpenOffice, so I got to go to a remote office location.
Are you already on the WebEx?
Mm-hmm. I just try to use this. Yeah. Why don't you drive?
Yeah, I
Sure,
did.
so.
Well, the interesting thing about the wind is that even, I just opened up Richard's SDI papers because I thought I remember this, but they don't know if even the GC. They have that wind. And they say, Mike, I don't know if you, while you were talking about the relative importance of wind, I pulled up the paper that Richard Seeger and his group had done with calculating GCM data.
Right.
And they actually set wind speed to be constant. They don't
There's a weird
even
lag.
take it.
Yeah.
And I don't know if that's because they think they can't get it.
Yeah, the wireless is very highly variable.
The land manager stuff or the biologist stuff is pretty possible. So they'll give you these anecdotal observations like, you know, if the wind picks up for a couple days, all those wetlands dry out.
Oh, yeah.
You know, so it's like the wind is really important, but somehow it's not.
It's super hard to model. I don't know what
Is wind in?
Okay, so why don't we let Kyle run through some of the soil watt stuff he's doing, which is related to North Central, I think through the foundational science area with the Lownroth.
Depends on the project.
Soil
Yeah,
watt.
we'll probably, let's flag that.
So I'm going to talk about soil watt, which Jeff briefly introduced. Soil watt is it's actually a sister model to Century, put out by the same sort of group of people. One of the Parton models from the late 70s. It's sort of been in continuous development since then and being amended to include more and more relevant things. So I've been using soil watt to simulate drought-related variables that I think are important in my cheatgrass demographic modeling work that I'm doing here for the North Central Climate Science Center. So I only have 10 minutes, so I'm not going to talk at length about soil watt itself, and honestly, a hydrologist would do a better job than me anyway. I'm going to talk about why I think a mechanistic hydrology model is useful, and then briefly introduce soil watt and what I've done with it, and talk about where other people can get it if they're interested in employing it. Okay, so first up, why use a mechanistic model to describe drought effects? I think everyone has an intuitive grasp of what drought is, or at least simple drought is. It's a sustained period of dryness that affects a site or a landscape. And we're interested in taking drought, simple drought, and scaling it up to the level of plants or ecosystems. And really, that moves beyond a simple explanation of drought and goes into talking about ecological drought. So what we're interested in terms of modeling, in terms of ecology, is describing ecological drought. So if I want to put on my ecophysiologist hat, I'm going to talk about how, from a plant ecophysiology perspective, we consider drought and drought effects, and how I think that we should describe it in terms of our species distribution model. So if you talk to a plant ecophysiologist and you ask them to describe drought, usually they'll talk almost exclusively about transpiration, depicted as EL up there on the plot. And a physiologist will treat transpiration as a function of atmospheric demand and stomatal conductance. So atmospheric demand being usually vapor pressure deficit, and stomatal conductance being the mechanism that a plant uses to limit transpiration so that it doesn't wilt under drought conditions. So honestly, when I work or think conceptually about building species distribution models, it's really this physiological control, this stomatal conductance that is in the back of my mind. I try to think about species in terms of being isohydric or anisohydric, tightly regulating their stomatal conductance or not ignoring it in terms of trying to define their drought response. And I think that that's the kind of outlook we should take when we consider drought in species distribution models. So when we build SDMs that include drought as an explanatory variable, we make the assumption that the suitability predictions from these SDMs reflect that physiological control component of species drought response. So this mechanism of transpiration, where transpiration is a function of atmospheric demand and stomatal conductance, is a simple representation of drought response, at least from a physiological perspective. If you really want to understand how plants respond to drought, you also have to understand not only the atmospheric side of sort of drought response, but also the soil side of drought response. So I had introduced stomatal conductance and atmospheric demand in the top in the previous slide. Soil conductance is represented there in the bottom. Really, the formulas are very similar. So the output, you can set them equal to one another, integrate, and derive a new expression for stomatal conductance that integrates all of these factors describing conductance from an atmospheric perspective and from a soil perspective. And really, it's these variables that are captured there in blue that I think are important to focus on in terms of species distribution modeling, and that I try to capture. I think I want to focus on. We'll get into this more later, too, when we talk about sort of goals or ideas for how we characterize drought, at least in SDM. But going forward, a lot of my work, I've sort of left out. This mechanistic model is complex, more complex than a lot of the statistical correlative SDMs that we build. I think that we can get away with simplifying it. As long as we just focus on some key variables, we can carry through the kind of mechanistic or implied mechanistic relationship described here in our correlative SDMs. So I've been focusing on using soil water potential and atmospheric demand as explanatory variables in my SDMs. And I've been simulating these variables using this mechanistic model, soil lot. So soil lot, essentially, I'll give you the dog and pony show version. This is a Java version, a Java front end for the model that we're putting together, and we're going to try and make available through the SOM interface. Essentially, how soil lot works, as depicted here, is you take a series of site-specific parameters, things like aspect, elevation, a range of soil water content that you think is appropriate for your site, something that you would get, for instance, if you were doing actual field work and collecting information on from Dobbenmeyer plots, for instance, or site variables, something that you can use to parameterize this model framework. So after you collect your site parameters, you specify the soil layers that you want to run your model at. Soil lot supports up to 25. Most of the systems we work in are not that complex. That has 8 depicted because I think it's actually along an ecotone boundary. So this is capturing shrubs, trees, and grasses. A lot of us this would be even simpler. You'd only want to characterize maybe 3 layers of soil if you're working with grasses, for instance.
Wait, these layers are soil, or they're different plants?
Yeah, well, they're different soil layers and plants capitalizing on those different soil layers.
So depth?
So it's depth.
Okay.
Depth and volume.
Okay.
And soil lot essentially takes these site-specific parameters and then stimulates how water moves through that landscape and through these different soil depths on different intervals of time.
So can I ask you for these?
Yeah.
It says, for example, tree, shrub,
Board. Yeah.
Yeah. For that was actually specifically measured at that site?
Yeah, well, those are empirical variables that are fit to those sites. So these are empirically derived variables.
Because something like Vic has something similar, but it's implied everywhere, right? If the vegetation type is a certain, correct me if I'm wrong, Ben, but if the vegetation type is some sort of forest, it does the same, it applies the same soil parameters, right?
Are you asking me?
Yeah.
No, it does not. The two are decoupled, or they're separate, yes. What it does is it provides a root zone sort of distribution, which is then interacts with the soil. Yeah.
Right,
but
right.
Yeah.
But you don't go out and do that differently every place. It's a function of soil type and vegetation.
Is what?
In Vic. Vic, you don't actually go, it's actually based on actual measurement. And you're saying this is actually based on measurements.
It doesn't have to be. If you have those data available because you're actually doing field studies, which a lot of physiologists do, and that data is available, great, use it. But if you have derived products from like satellite imaging or some sort of simpler model that you've applied, you can bogart those data and parameterize the model the same way. It really depends on how nitty-gritty you want to get.
Yeah, a lot of the soil survey data goes into like default soil parameters for these models, and then from there they're adjusted if there's a reason to believe that they need to be. For hydrology models, that is.
All right. So after you specified your potential soil layers that you're interested in for your site, you give approximations for vegetation cover. Once again, if you're doing this on a site-by-site basis, you'll have done Dobbenmeyer plots and have at least Dobbenmeyer scale scores for percent cover for your focal species that you can then use to parameterize the model to characterize transpiration. You can also get these from derived land cover products if you don't have site-by-site information and you want to run this across the whole region. You can fill in the blanks or approximate using land cover data. So after providing a good indication of what plants grow at that location, you feed the model with daily time-step weather observations. You can get these from station data if you're working on a site level, or I have used a lot of DayMet data or the Maradol daily time-step data set for some of this, where I pull extractions for all of the sites covering, for instance, Western North America, and then parameterize my runs that way. It kind of depends on you, but you can run the model under current or future climate conditions depending on the data available. And after you specify weather runs, the model goes through and simulates on a daily, weekly, monthly, or yearly aggregation a series of variables that characterize AET or PET or soil water content, soil temperature at different depths, things that are meaningful to plant physiology that satisfy the variable demands that I had outlined earlier. Essentially, using these data, you can produce gridded raster products. This is I usually do it. That you then throw into your SDMs as an explanatory. So right now we have an R version of SoilWatt available. If you know how to program in R, it's fully integrated. We also have the Java version available, which runs on a site-by-site level. That was the GUI interface that I just showed you. I'm working right now on integrating our R version of SoilWatt into the SOM. The SOM can call this R SoilWatt version, generate a gridded raster product, and then the SOM can just bogart that raster product and use it to build an SCM. So it is available, but not quite yet. Working on that, or I'm working on that.
Do you have an approximate schedule on that, or because I'm wondering if project is interested in plugging into it, but maybe we can table that.
Yeah, that's up to you guys. I'm working on it now. And the R version of SoilWatt is stable, so really it's just a matter of chugging through some Python and getting it to interface properly.
Might have some beta testers with the surrogate species project. Be curious.
But that's all I've got. Okay. Yeah, you can get it. You can get SoilWatt and our SoilWatt up of University of Wyoming's GitHub repository. So if you just Google University of Wyoming and GitHub, we're the only people at the University of Wyoming who have a GitHub. So yeah, you'll find us pretty easily. You can get the Java version that I demonstrated here and there, and the R version, if you want to play around with it. And if you want help setting it up or parameterizing your own runs, email us, and we'd be glad to help. The more people we have involved bug testing this, the better. Thank you.
Good, thanks, Kyle. Joe, I guess we'll switch over to you to sort of kick us off on more of the discussion section of this. You got pre-material, I think, if you follow you.
Oh, I've got a little presentation, and then make sure I've got it up here. And then I'd like to let's see, let's make sure I'm on. Do I have to accept this something?
I got to make it presenter first, and then you can.
You are now the presenter. Share my desktop. Okay, I've got. Let's just. Sometimes it takes a while to come up there. Sometimes it takes some magic interaction there. Let me watch the time pretty closely here.
About 5 after.
5 after.
And let me just check in. We've got a 1 o'clock meeting with CNHP. Is it just Karen and Michelle, or others come from CNHP?
Yeah,
So we could possibly push that back a little bit. You know, I'm on the leave room to run to lunch. So we could go till possibly 12:30. Does that present a problem with anyone? And then, do you got to get on? You got an airplane? Okay, so I think that relieves a little bit of pressure.
So we've got a pretty hard stop later in the afternoon.
Okay. Yeah, and you wanted to be part of the CNHP. When do you guys have to leave?
I'm going to be part of the CNHP.
Yeah.
I'm going to be part at the very beginning.
Didn't know about it, and I've got something else I have to finish
Okay.
this afternoon.
So she's driving back with me, but working here while I'm at the CNHP meeting.
Okay.
Although you may step in at the
I
beginning.
may stay for a little, I'll be in for a little
Okay.
bit.
I thought I wanted to bring it. You know, we talked about a bunch of different spatial and temporal scales and uses, and I wanted to bring it to the sort of largest scale and longest time frame that we're going to be considering here, and that is climate modeling and climate projection. And what I want to come out of this is just understanding why we set up, why typically when you do a response, a climate change study with a response model, such as a hydrologic model, such as an ecological model, or a hydroecological model, why there are a couple of ways, a couple sort of methodologies or grand methodologies, if you like, that people follow, and why. And the biggest problem comes because of 2 reasons. When you're dealing with climate models are physical models based as much as possible on physical principles. They are not that heavily calibrated. As a matter of fact, they are not calibrated regionally. They're calibrated at all in terms of the global integrated energy balance on the planet. So therefore, there's going to be a lot of regional differences. And the reason for that is we want to keep as much physics in there because we want all the physics in the model to be responding to the changes in greenhouse gases. We don't know how it's going to be different in Antarctica versus, you know, the Great Plains, and we want some universal principles, or at least as universal as we can make them, based on as much physics as we can put in there to get the differential responses between the places. So, because climate change is fundamentally global, I mean, you put CO2 in, it mixes in the entire planet, planet's energy balance gets changed, the entire set of things like Hadley cells and jet streams, all the advection of moisture changes in the planet as well. A little bit at first, and then, you know, more later in the century. So I was talking about climate model biases, not so much where they come from or what they are, although I'll show a tiny bit about that, but how we deal with them in practice. And so this is just an example of climate model biases. This is just a precipitation map, a climatology, let's just say, from the historical period, in this case 1911 to 2005. And what we've done is taken, and I forget how many climate models in the sort of multi-model ensemble that we have currently called the CMIP5 ensemble. Taken the ensemble mean of that, just to show you what the mean bias of these models is. And this is in this case, in terms of millimeters per year. And we subtracted off an observational product. In this case, I believe it is the PRISM product because it goes back to 1911. But I wanted you to get a sense of the magnitude and the location of precipitation biases. Now, great, prairie potholes, I mean, you're on this region where there's actually, in the mean model, there's not that much bias, although there's, in any individual climate model will have a spread of biases around that. But when you start working more over towards Wyoming and Montana and Colorado, there are some models that have more than twice as much annual precipitation. And in different seasons, these biases can be pretty large. In fact, every single model I looked at for the state of Colorado in the CMIP5 ensemble had too much precipitation, although some only 20%, that was a good model, some 200%. Reasons for this, I didn't want to go too much into that. It's not just the fact that the mountains are not very well resolved, because they aren't very well resolved. The finest scale models are right now about 70 kilometers, which gives you about 10,000 feet for the top of the Rockies, but the coarser ones give you about 7,000 feet for the top of the Rockies. And narrow mountain ranges, particularly like the Sierras, are really not very well represented at all. But that's a bias even on the coast and at the coast here. There's just too much moisture coming into the coast of California. Here it's more classic. You have too little rain where you're not resolving the mountains, and too much rain where you didn't stop the rain shadows. This is really kind of classic what you expect, but really it's just too wet everywhere here. The jet stream is slightly positioned wrong and is too moist, and that's basically what I want is why it's pouring too much moisture into what otherwise is a fairly arid region by world standards. So the implication of this, I mean, what? I mean, eventually we want to improve the model so that this doesn't happen, but we don't want to do it by just forcing it to be that way. We want to do it by improving all of the physics, and this may mean improving the ocean physics in the tropics to get a better El Nino so that this improves. I mean, the whole system is coupled globally when you look at climate scales. It's a very difficult problem. Matter of fact, it's not just El Nino, it's some of the deeper circulations people think in the tropics that are leading to some of this other things. So this leads to a problem that if you just took what we want, and I think Helen said this, we want consistency between the historic and future results in our climate change studies using ecological models, which is said in more blunt language. You can't just take future climate data from GCM, run it through your ecological model, and compare it to results from the historical observed data. You can't just put the two together without, lots and lots of checking to make sure that's true. But even then, you wouldn't be able to. Why? Climate models have biases in their historical simulations that I showed you. So what? There's another reason, and that you can't train your ecological models directly on climate model output because climate models don't track the same years as observations. Climate models have been started in some ancient time period, probably in 1980, when they started spinning up the models and then sort of chained them on one to another. They are free-running simulations. They are only affected by external forcing, like things like solar radiation. They are what we call external forcing, things like volcanic eruptions that put aerosols in, and things like the composition of the atmosphere, which will determine, well, I could go into that. There's two ways we do that, but the composition of the atmosphere is also considered, for our intents and purposes here, an external input. There are models that do that internally. Okay, that's not really what we're dealing with here. So, yeah, 1983 is not 1980, in the model is not 1983 in the real world, except in the sense that it has the same greenhouse gas forcing, it has the same volcanic forcing. So, yeah, you did see El Chichon in that year, which was a big volcano. It did cool the planet by several tenths of a degree, and you can see this in the trace of the observations. You can see that in the trace of the climate models because that's an external forcing. But you don't see the 83 El Nino in the climate models. You see El Ninos all over the place. Maybe it's an 82, 83. But it's a free-running simulation for all the stuff that happens, what we call internal to the climate system.
Because there's not an ocean forcing in the model.
Because the ocean and atmosphere are let run free, and they develop. And in the modern set of models, we do actually have, well, some of them have decent, what I would call decent El Nino simulations in them, although it depends on how specific you need to be about the power spectrum of them. Compared to the last set, they're much, much better. And
by power spectrum, you mean the periodicity? Yeah,
the periodicities. I mean, we're the dominant periodicities of El Nino. So you do get the phenomenon. You do get many aspects of it, such as the spatial patterns and the periodicities, the power spectrum, if you like, the autocorrelations. But you don't necessarily get it to line up because it's really very, very weakly affected by external forcing. So some climate, the impact is, the other thing is that biases may lead to nonlinear effects or impacts in your hydrology and ecology models. I'm specifically worried about a lot of these response models because they have a lot of nonlinearities in them. I should say nonlinearities or linearities in the things that we don't put into our models. So they may be sensitive to autocorrelations. They may be sensitive. They may have, some of these the sort of correlative models. Even they often have very, very strong cutoffs in some of the variables where you have, for example, temperature, you might show a really narrow temperature range when you do some of the plots that are wonderful that I've seen on that screen. So this worries me a lot, that if you are not careful about how you handle this, you're going to end up with discrepancies, and I'll tell you what I mean by that. So some climate data products have been bias corrected. Bias correction only goes so far. I mean, they often bias correct in the monthly means, or they bias correct in some sort of probability distribution of monthly means, but they don't bias correct in autocorrelation. You really wouldn't want to go that far. You don't really want to. You can try to force the square peg into the round hole somewhat, but you don't really, really want to be whittling it down to a round peg, because then you've lost the climate model aspect. So this talk is not about where biases come from, but what we do about them. So we're going to be focusing a little bit on the bias correction here, but I think in a couple slides. So two main methods. I mean, this is really simple, what I'm going to say next, but it comes across as a little bit more complicated than it is. There's the delta method, which is you apply a change factor applied to historic data. It's really simple. I'll get to that. The second one, which I've been calling for Helen, jump to model world. You use the bias correction of the climate model data during the historic and future periods. So you calibrate your response model in the real world, then you jump to the model world and do your comparative study of past and future. And that gives you nice.
Don't change it yet.
Pardon me?
Don't change it yet, I wouldn't.
Yeah. So this is sort of at the level of, methodology. I mean, a meta-analysis of methodologies, right? This is the two kinds of things we do, roughly, just to get consistent comparisons between the past or present climate and the future climate, so that you don't have effects that are determined by jumps at that boundary. Right? You want the effects to be only determined by the things you've changed. I mean, underlying all this is really, really that simple a concept. And knowing, are you ready? Yeah. Yes. So, I mean, delta method, you calibrate and validate your ecological response model in the historic period, just as you always do. You calculate some sort of change factors for the model inputs. In this case, I'm thinking about the meteorological model inputs, based on how the climatological averages show the differences between a period of future and a past. So warming by 2 degrees, or warming by some field that's degrees here, 4 degrees here, but spatially varying. Having a 10% change in precipitation over Iowa, but a minus 20% change over Arizona. You apply these change factors to the model inputs and run the model, and then you have your nice comparison. So the baseline for the comparison is what you did in your observational study, observationally based study, modeling study. So you have your statistical model applied to your observations. It's your baseline. The change is this change factor. So the temporal patterns in both future and past, come from the historic observations. So things like number of rainy days, typically you don't change that, which is a downside to this. You have to be kind of confident that that's not a dominant change that you're worried about. The spatial patterns of change come from the climate model and are typically at the large scales of the climate model, 1 degree, 2 degree, 100 kilometer, 200 kilometer fields. You see the spatial change is applied there. So you tend to do percent change in precipitation. You tend to do absolute change in temperature. These fields tend to be fairly smooth from the climate models. They tend to be smooth on a grid larger than the grid of the climate model, so you can be confident that applying these smooth fields is not such a bad thing. But you lose a lot, right? So it's useful for period-to-period comparisons, where you just kind of want the broad brush climatic forcings, and particularly are pretty sure that these kind of broad brush things like the warming in temperature is going to dominate, then you might actually want to use a method like this. It's very simple to apply, and you can always do it as the first case to get a sense of what's going on. It also can be used when you just have station observational data. You could just do a change on that. What if it were 2 degrees warmer and 20% wetter, right? But it leaves out a lot of the details, such as change in number of rainy days, changes in variability, and other details. And you have to
It's that.
Well, let me just say, I mean, to choose these delta factors, these change factors, you know, that's a little bit of an art to actually represent what you want to do in the future. But it avoids an important one, and this is why an important hydrologic study in the state of Colorado is being driven by an engineer who knows his stuff, and he's chosen this method because it avoids model biases during the historic period caused by the fact that there's all these nonlinearities and others knock-on effects that aren't captured by the bias correction. So if you really, really are important about your timing of El Niños, it's really important to get the 2-year droughts just right, then you might want to actually just take your historic period and assume that that's not changing in the future. Because the climate models may give you a poor representation. Or it may just be that your stakeholders that you're dealing with don't trust that, which is the case of the Colorado study. They trust the historic, so they're going to do a historic plus delta factors. It's best thought of as a sensitivity study guided by the magnitudes of change seen in GCM. Sensitivity study, you're changing a couple of your input parameters. How much to change them? Well, by the patterns and magnitudes seen in the climate models. Most often applied to changes to temperature and precipitation, but then how do you get something what Helen wants, which is a consistent change in potential evapotranspiration out of this, right? It means that you probably want to have some sort of intermediate or empirical model, such as this MT-CLIMB model from Montana, from Steve Running's group, to derive variables such as humidity, radiation, and potential evapotranspiration for use in the response model. So you want some way to get some sort of consistent set of inputs for the most important ones, and this is one common way to do that. You could, I suppose, go into the climate models, particularly for wind. You might want to do a delta factor on winds just based on the climate model. I think that would not be a bad thing to do. But otherwise, you want something that provides you with a somewhat consistent set, and I think that might be the best way to do it. But I think I've seen it done this way. So let's go to the jump to model world thing. And this is going to be pretty much, when I get done with this, I think I'm just going to go into the discussion. There's a couple other slides after that. It's more complex. But I put the summary up here before. The baseline for comparison is the downscaled bias-corrected GCM climate model fed through the response model. So no longer is your observationally driven model your basis for comparison, right?
But it's historic.
It's a simulation of the world with historic amounts of greenhouse gases ahead,
Right.
and historic amounts of volcanic forcing, aerosols, and stuff like that at the climate model level. But it's still, so the temperature should be, 2 degrees or 4 degrees cooler than the later part of the century. You still have the temperature contrast, but you might have a little bit of an offset. Now, these have been bias corrected usually, and let me run you through the steps. And I hope this makes sense logically. I mean, the first step is you just do what you do, right? You calibrate and validate your ecological response model or your hydrologic model based on observational meteorological input and then your land surface input and all your other inputs, right? You run the response model using the bias-corrected and downscaled GCM outputs. Now, you have some of these available in the North Central data realm. You have this at the GeoData portal. And the inputs to the response model for the entire period, including both the historic past, say 1950 to present, and extend out to the projected climate into the future, say the present out to 2100 following the RCP 8.5, the high emission scenario, for example. Then you can actually do this following a medium or a low emission. You have a consistent set of climate model-derived inputs. It comes along, and then for temperature, it goes up, right? And so you have a consistent set of inputs derived from the climate model. Step 3, which is not always done, but I will tell you a little story after this, is to compare the results of the response model with the GCM inputs to the observation force response model, the thing that you did to begin with, right? Are they even different? Well, you can't, they're not lined up in time, so all you can do is compare them statistically in terms of their distribution-wise comparison. Because the temporal sequences are not the same order as in the observed world. This is often skipped. For the Colorado River Basin Supply and Demand Study, when this step was first skipped, they went back and looked at it, and they noticed that the difference between bias-corrected inputs from the GCM into their hydrologic model and observed inputs, which nominally were the same on a monthly time scale, was 1 million acre-feet out of 15 million acre-feet. And that was kind of disturbing to them. They thought, oh, we used bias-corrected inputs, we should get the same annual flows average as our output. So they ran the hydrologic model again with observed inputs that they calibrated the model against. They got something like 15.8 million acre-feet for that particular period. They ran the same period, bias-corrected climate models, bias-corrected to that climate. The monthly averages were just the same, and they got 14.7 million acre-feet or something like that. And it was a puzzle, and it had to do with. There's a couple things it had to do with, but one of the main things it had to do with was the climate model had different autocorrelation statistics, so that affected the hydrologic efficiency of the system. And okay, you could say 1 million out of 15, that's 7%. That's pretty good, right?
Yeah.
I mean, so if that's your viewpoint, if you've got errors that are much larger than that, and 7% is just a small error, you can just live with it. 1 million acre-feet on the Colorado River, people were screaming like, "Where's that? It's my million acre-feet." You have to really have an explanation for this. So this is a real-world concern that is not always looked at, and I'm really worried that in the nonlinear, these ecological models, you may come up with some interesting, or maybe not, but you have to check it. So the step 4 is there will probably be some differences, and evaluate those. Often just difference in means, maybe just, Helen and I were talking about some very simple ways to do it, just looking at some histograms and comparing them and doing, difference in distribution tests, they call smear up and other difference of distribution tests. But probably simpler to do just binning and counts versus our drought years handled similarly, our wet years handled similarly, or our high bird count years handled similarly to low bird count years. If they're acceptable, then usually what you do is if differences are small, then you could just jump to model world and say, well, I'll use the model world as my baseline, and I'll use that as my future and do that as my comparison. So I get 20% reduction index in the model world, right? Or I get a movement north in a certain species in the model world, and if this difference is really disturbing to you, if you get like 100% difference or 50% difference, then you realize that somehow the predictors have been set in such a way that that the bias correction of the climate model isn't bias correcting enough. I don't think that's going to happen, but with a new set of models coming in here, you have to test it. And then make sure you look at climate projections for more than one climate model. The nice thing is you get a nice envelope of variability from the past. The envelope of variability goes out into the future and kind of widens. You get a nice way to go through uncertainty. Now, I'm probably at where I want to be here for the discussion. But there's one more point I wanted to make, and this was going back to the original topic of we have consistency between past and future, but how do we do that for these ET variables? Now, this is, I assume someone would show this. This is Penman-Monteith and Thornthwaite Palmer Drought Severity Index. Just for the historical period, this happens to be a global average. This is from the Justin Sheffield's paper, et al. Paper. And it just shows that Penman-Monteith shows a negligible decline in PDSI, negligible increase in drowsiness is down. Thornthwaite shows a significant increase in drowsiness. So this is what got me going on saying we have to get ET handled correctly into the future. You don't want to be assuming you're going into a future like, if you take this out into the future, this divergence continues, right? And we don't want to be planning around this when that's more physically based. I won't show this. Mike, you've probably not even seen this. The Priestley-Taylor coefficient, it declined in the future in the climate models. This is just an indication that the processes going into the evapotranspiration, evaporative demand, potential evapotranspiration, the balance of those changes going out into the future. It behaves more like an equilibrium ET calculation. So it's probably more radiatively driven over the whole globe. I mean, this is a global phenomenon, but you know, you can see this is number of models agreeing on that. So basically, it says that almost all models are saying that the processes change in a particular way.
This says the PET itself is due more to radiation than to temperature. Is that right? Or will be?
This was just an odd analysis, but I thought it was really nice because it showed that it's kind of a global phenomenon that you have. The Priestley-Taylor method, which I assume someone would mention, but you didn't, is just you have a coefficient times some sort of equilibrium for PET where you have, you know, no fluxes of moisture or very little fluxes of
There's no effective component at all, yeah.
Right, the effective component kind of is it goes to 0, and then you have a radiative. And it turns out this is like 1.26, but it's 1.7 in arid areas, and 1.2 up to 1.5 or 1.6. So it says that you actually get more evaporative demand due to these effective components, and it's roughly 20 to 50% more than you would get just from this equilibrium radiative component. If this coefficient declines in the future, it says you're approaching this equilibrium, and that means the effective components become less dominant, the radiative components become more dominant.
That means temperature becomes more important. Sorry, I'm just
Well,
adjective
yes,
radiative thing.
Kind of cloudiness. Kind of cloudiness and long-wave radiation becomes more important. Now, whether that ends up being dominant, I don't know. But this is a really nice, to me, an indicator that stationarity is dead in the calculation.
And would you say they become more important than the advection, the wind?
Become more important than they are now.
Okay.
And it just indicates that, as I say, stationarity is dead in terms of calculation of PET, the other quote on the other wall, and that you had better be looking at all the physical drivers and then sorting it out later rather than assuming you know what physical drivers are really going to be doing this.
Okay, so it's not necessarily more important than advection, but more important than they are now.
More important than they are now.
Got it. Okay.
And I just put this up there to just as another indicator that things are changing. So I want to go to well, this is sort of the practical discussion, and I don't want to skip that because that's the end, but I can do that as part of the discussion. And Helen, did you want to help? I mean, I assume you wanted to. How did you want the discussion to go? I'd be happy to help lead it, but it would be nice if I had you to represent the demand side of the information equation here.
And I think other people can too. Yeah.
I think that, this has been a whirlwind tour, and as Joe said, this is the start of a conversation. The driver for this meeting was a surrogate species project, so, there's kind of deference to that project, getting your questions answered because of some deadlines and some timelines to get some stuff done by the summer. Although other modelers that are here, can definitely chime in or at least, listen. But I think that really by the time, and I think, if we could go, let's assume we can go till 12:30, and we'll break for lunch. Let's make sure that you have a game plan, and you're happy with taking advantage of the hydro and ET and climate modeling folks being here.
Yes. So before we get started, one thing I put together before I came here, but didn't complete filling out, is sort of a table of the kind of ET, PET, and so I'm mixing a lot of things together here. ET, PET, or ET, the demand product, and drought index, which includes, of course, the precipitation component. All these data sets that are kind of available for use in this area.
Is that bigger?
Unfortunately, let me just see if I can, let's just see if I can, I can't make it bigger without doing this, which maybe I should do.
So you will.
Not going to do it.
Right.
Oops. Pardon me?
Yeah, that's bigger. Yeah, that's fine.
And you will distribute this too.
Well, what I wanted to talk about was how to make this information. This is going to. You're just going to get a sense of what's going on here since
Actually more of a conversation, and we'll probably see a version that comes out of the conversation that's about to happen. Yeah.
Hoping that this would be like all on my screen there, like that. So, this is so I wanted to talk about sort of three broadly types of products that we have discussing here. And I wanted to make sure we don't forget products. One is remote sensing. And you get a lot from remote sensing, not just ET and PET.
Uh-oh.
I'll do that.
But I wanted to mention an important set of products that we haven't that been only tangentially mentioned, and that is the MODIS product and the improved MODIS product that Steve Running is generating for this group as part of his last funded cycle. So very much it's similar in many ways, but also different from what Gabriel was talking about. But in the spirit of a remote sense product that depends on surface temperature, at least some of their products do, and that uses an atmospheric reanalysis model, so data that's been put through a model to calculate some of its meteorological inputs. You have remote sensing measures of usually of ET, it's usually put out some sort of PET, which is usually a Penman-Monteith-like method, and then there's other things like gross primary productivity and all this stuff that they put out. So let's focus on these products. We have a set of, let's call them, well, I don't know if you want to call soil water land surface model, but I'm talking about a physical hydrologic model of the soil. So we call it land surface model, physical hydro / canopy. We have that, and then we have related to this, but I'm going to talk about the climate models. The other person not on this call, which we've been having conversations with, and Helen has, is Richard Seegers, and Andrea's a part of that project. And so an example from this is that you may have caught that he has created a Penman-Monteith PET, PSEI, and a PDSI. I'm going to call it dash Penman-Monteith.
Well, I don't think he served the PET, so I asked him that, like, could you, like, I think they might have thrown it away. I mean, obviously they had to have had it at some point. But if you look at what their net PDF files, which ones exist online, it looks like it's just the PDSI and SCEI, which is too bad.
And so, I mean, the two sort of products we have here are MODIS, MOD 16, and then the improved. Let's call it the improved MOD 16. And then we have what's your acronym? Was it the CBOP? CBOP?
Hey, Bob.
SSEB. Oh. SSEBOPS. So, and then for land surface modeling, you can download. There's a couple of things that are coming out now. One is from Bureau of Reclamation using VIC. Actually, it's from Ben, right? Ben?
Hi, Ben.
Maybe.
He might be on mute.
So, I mean, Ben is creating a data set of PET and some other variables that come out of a land surface model, and then we have the others. But the other one may be interesting here. I know that the NASA NEXT. This is this downscale data set, climate model data set, has been run through the TOPS model, and I know that produces this. And then we have now these soil watt. And that's at the present kind of a do-it-yourself. You have to find your inputs, but it would conceivably be possible to create a data set from that.
Joe, there's also NLDAS runs 4 models to produce ET NOAA, Vic.
National Land, North American Land Data Simulation System,
Yeah.
2 probably is what you want.
Yeah.
And there's a bunch of other things here, but that's just historic, right?
Yes, 79.
The nice thing about some of these two, is that these are historic, and then they also come with projections. And these are also historic and projections, but the historic part is just from the climate model. So I'm trying to, what I want to do in this table, not here necessarily, is find a place where I could build this out, and build this information out in a way that's usable for people. So the first question is...
So could you just confirm again which, you said that some of them, that it's just historical, but the others don't, both?
Yeah, I have a column in here where it says kind of historical simulations, meaning from the GCMs, historical, based on observations, and historical and projections. I mean, I haven't quite filled that out, but the idea is that some of them, you know, I mean, the time periods for the remote sensing ones are, 10 years, 15 years maybe, right? Except for the Landsat, you can go, if you wanted to and had the money to do it, you could go back to 80? 80. But most people don't do that, right?
No, it's expensive.
You see, that's expensive to do. But so for a small study set, you probably could, but nationwide, you probably couldn't.
And Gabriel, are your data available? What's the time span that you've done already?
Modus is since 2000.
Okay.
That's the one that's operational. But
And that's the 1 kilometer. Yeah.
But yeah, for specific study sites, then Landsat since the 1980s is possible to do.
But you also have a couple of years of the 100-meter done for everything, right?
Right, for selected basins like Colorado and Delaware.
Okay. So, okay. That's why I happened to be lucky in the Colorado River, because we got to look at them.
Right.
Okay, so I guess I wanted to open the discussion here to trying to synthesize what we've said, meaning that, we want to use the best data sets to calibrate our models. We often have to use site-specific or region or very small physical, spatial scales to calibrate the model, or at least you want to, because you want to explore that kind of detail. And yet, when you get to successively to the larger scales here, and these tend to be, several kilometers, and these tend to be 100 kilometers. How you choose the best way of using this data, and I have, a couple options are, well, you just choose one of these, and you just do this jump to model space with the NASA models. You just run them and do that.
So to just take the work that Helen has described as kind of a test case here, and sort of maybe stepping through some of these decisions with the constraints of the needs of Valerie and Helen on the project. One of the peculiarities of the modeling that they're doing is that the bird data, which is ultimately going to be the modeling that we're going to be doing, is applying it to the bird data, kind of dates back. I think we probably wouldn't want to go, we'd want to go at least back to 1980, wouldn't you think? So we're using breeding bird survey data that actually dates back to 1966 to present. If we just jump back to 2000 to present, we're going to lose a lot of signal because these bird distributions have already probably changed. So we want to go back at least to 1980.
It's not that they've changed, it's just that we missed the dry years, too.
Yeah, we missed some ecologically important data. So going back to 1980 would be really nice for this project, which then, I don't know if that kind of reduces that list to just a few that we can use. I know that if we jump to model space and the climate models, the world is open. But
the world is more open that way, although not all of these sort of downscaled, bias-corrected products go back that far. Some of them only go back to 1960, some of them go back to 1950.
Okay, so some of them do go back that far.
To 66, yeah.
Yeah, so,
great.
I mean, my view on something like this is, my goodness, this bird data, and assume the pond data as well goes back that far? this bird and pond data is like amazingly hard to get and amazingly expensive.
To collect, you mean, not to
But you should use everything, you should, this is one of the decisions, how much, is it, I think it's a small compromise to use a different, maybe slightly less precise meteorological data set.
And also,
incorporate more of this.
yeah,
Sure, that's what we were talking about.
So,
well, and also,
that's your decision, but I would decide, I would go
Yeah.
with the.
we should try to figure out how you can use as much of your ecological data as you can without us being, especially Joe being and Mike being uncomfortable with what we're doing.
Exactly.
Because my understanding of the ecology too is that you've got birds that live several years and pond cycles that go over several years. So, really having a short, even 30 years is a pretty short amount of time for doing any explanation.
So you showed that correlation between PDSI and pond counts. What is the PDSI, and that was just, Thornthwaite PDSI, I'm sure.
Mm-hmm.
What is the PDSI, what do the ET people think of that? I mean, would you then, what do you think, what does it bring to your mind as far as using these predictors as sort of, what scales you might want to use?
Well, I'm inherently uncomfortable with PDSI as it's currently formulated, just because it has a super simple hydrology model, and it has a temperature-based evaporative demand model. But that said, in your area, temperature is one of the most significant drivers of evaporative demand. So you might get away with that.
And I don't think PDSI is easier or harder to get than, like, either PDSI or SPI can be calculated based on 10 Monte or a Thornthwaite.
Well, it can be, but isn't it a big, has it already been done?
But doing it in the Thornthwaite way, I think is pretty simple. Like, there's that R package that you could even run it that way.
Right, but I think we decided.
You wouldn't want, but doing it the other way, yeah.
So you could throw out that, you could say, well, okay, we'll improve this by making this 10 Monte. And one way or another, we'll find a data set to do that.
I want to throw out another option beyond your sort of your two solutions. I'm not sure how orthogonal or if it's a third or it's kind of like hybrid of kind of number one, is to fit a model with current data as best as you can to understand relationships, and then just pose scenarios in the future based on climate models. So instead of trying to apply an ecological response model into to 2050, just say this is what we understand the case to be. And now you look at the models and you say there's a certain chance of drought, or there's an increase in ET. And interpret it as just not necessarily putting your specific model, and that's kind of what we're doing with the Colorado Natural Heritage Program and the State Wildlife Action Plan, is just to say, here's the relationship, given current data, and then here's what some indications of those meteorological or abiotic factors are going to be in the future. So,
Not running the model, or running the model?
Right, not applying the model to data from 2050.
Just understanding responses to drought better, I think.
Right.
More or less.
And then saying, okay, so and then doing some connection with the climate model to say, a climate model shows, for example, maybe 2 years that it's dry, instead of one, or, and then you say, you average the models and you show an explicit relationship with current data to show, you lose acreage or you have this impacts on birds.
Could you do that in a spatially explicit way? Because I think that's what whether or not it can actually be given to them, that's what the clients really want, is sort of the spatial predictions. There have been models run, Carter Johnson's models that do say, okay, if it's 2 degrees warmer or 10% wetter, here's what we think. And it wasn't done in a spatially explicit way. And so some of our clients up there kind of go, well, they didn't run it in a spatially explicit way.
I think you can, but I think you have it at an 8th degree resolution. And so that's where you use the Landsat data and you really derive these relationships But you're stuck, there's no way around the fact that you've only got a 1/8 degree kind of resolution of what might happen in 2050.
With the climate.
So, I'd like to admit to that and just have a spatially explicit map at a 1/8 degree of some variable that would be.
That's fine for them. And I think, Andrew was a co-author on a paper, that Ballard et al. Paper, that actually showed that over the PPR there's not a huge gradient in the magnitude of, like, the projected increases in temperature and shifts in, because that paper split the Canadian portion from the U.S. portion, and we're just focusing within the U.S. portion. And I remember my takeaway from that paper was, like, there isn't, in terms of the GCM say it's going to get however many degrees warmer, that difference actually isn't that much, in Montana versus the eastern Dakotas.
So the scenarios might be a reasonable approach.
Yeah, so, I think, in terms of understanding better, and I don't know if this is possible, like one of the level of spatially explicit data you showed, I almost wonder if that's a better response variable than the pond data we have, could you can actually watch ponds evaporating, which that's actually data that is almost like a holy grail that we don't have in our response data.
What data is that? I'm sorry, I missed that.
Well, Gabriel's data, you could, I think that, and that might be the kind of thing, the kind of space for something like what you were talking about, Jeff.
So by Gabriel's data, what part of it?
Landsat ET.
Okay, so it's ET from the Landsat.
Yeah,
I just want to make sure I'm not misunderstanding.
Just like the link to the birds then would be there's this question of, climate change can affect how many ponds there are in May, which is what we have a response variable for, but one of the biggest effects of sort of projected change is this increase in summer potential evapotranspiration. And so what that probably means is that those ponds are sitting on the landscape for a shorter amount of time, and what his data might be able to get at actually is how long are those ponds actually sitting on the landscape, and even if that is, the shorter temporal resolution there, it might be something that you could link, ideally, that, if we could find someone with some demography data, that's like, you could
demography
really,
data like
birds.
Bird demography. Okay.
Yeah, because for ducks, for example, they often nest on the borders of these pretty small wetlands, and that's where ducks are at their highest densities. And as those wetlands dry out, they'll move to a deeper wetland. They'll bring their ducklings there, but they have to get their nets have to hatch with those wetlands so wet.
And they take a month to hatch.
Shortening of that period could be, being able to quantify that could be, that was when I saw your presentation, that kind of thing was what was like ringing in my mind, not like, maybe not so much as a solution to what are we going to use with our BBS data, but almost like, is there some potential for a better response variable there? So that's a little bit tangential, but I think actually also potentially really interesting that I wanted to mention while we're on the route.
Yeah, and I think that this hydro period question is, how long the wetland stays in the landscape is really one of the big issues for the client, because that they see the hydro period shortening and what implications does that have on the birds.
And you agree that your data could do that, right?
Yeah. And to associate that with duck nest survival data would be pretty cool.
And you have peak months you're interested in, or you can look at the whole year, but especially from May to September, that's generally more reliable.
Yeah, even to July.
So that's still getting at the question of could you have a better understanding of the recent relationship between drought or the variability and productive survival?
Well, let's go with this idea of how you would build a scenario, a climate change scenario from that. Suppose you have a response model and it shows between wet and dry years, the ponds, or warm and cool years, you have ponds that, it's a more nuanced version of how things evolve during the spring and summer, right?
Yeah. I mean, so the way I look at it, for example, the ET we model is Landsat, so it uses demand, evaporative demand. That's a certain amount now, but 50 years from now, it will be, let's say, higher. Then the drying of the ponds will be at a higher rate. So that's how you're going to incorporate that. Now, if you understand the distribution is like this, But okay, the drying rate would be faster, then it will disappear.
But what Joe's saying is, can you make it quantitative, not qualitative, I think.
Yes.
Yeah, and
Well,
I
do
think
you
that
have
it's
to? I think it's a good
really
question. You know, I think that,
Yeah.
what do your stakeholders need? And I'm just afraid of, like, moving towards quantitative gives almost a false sense of accuracy.
Okay, so using the full data set going back to 1970 or so for one part of the question, but then using the shorter data set for some, sort of a different question, like perhaps getting at this mechanism with hydroperiod and duck nest survival as a way to help interpret the scenarios.
One thing going into this, if you think of how the climate models show change in that region, I think one way to get through this is to pick things that we think are changing on large scales and use that as drivers for your model. An example is, even if you had a 2-degree Celsius warming everywhere, it's going to respond differently in a dry landscape than a wet landscape, right? It's going to respond, the hydrologic cycle in the mountains is very different in the high snow-dominated regions than lower down. And so you can have a very fine-scale response based on the landscape to a very broad-scale climatic forcing. So you might want to say something that PET itself is a very broad-scale variable. I'm just suggesting that winds are going to be changing over a fairly large region, especially if this region is fairly flat. I know there's mountains, there's river valleys, and there's convective winds, which are the hard thing to get at. But so you might want to suggest that things like winds, solar radiation are going to be changing on a larger scale than the 8th degree grid. There's going to be a relatively smooth, something like PET, not ET itself, because ET is determined by all the fine scale, but something like that driver. So using a PET, or in this case, I would argue that precipitation is going to have fairly large scale changes as well on climatic time scale. So using something like what you're doing, which sort of the PSEI, which is P minus PET, and then normalize. Might be just fine. I mean, you're saying it's something of fairly broad-scale driver of drought in that region. And then you can let the little statistics, the fine scale that you're getting, which include land cover and regional pond counts and things like that, do the work. I'm just sort of suggesting that. But you're suggesting doing this in a scenario-based, like putting 2 droughts back to back?
I'm not sure if that's what I was suggesting. I just thought that you could lay it out for managers in terms of look at the climate model to lay them, kind of give a range of plausible scenarios. Given this is our established relationship, from the current data sets, and then say what's going to happen in 10, 20, or 30 years is a range of possible options from the suite of climate models, and then derivatives from those.
So, for example, if you thought PET was going to increase by, I don't know what's a reasonable percentage, 5% by 2020 and 10% by 2040 or something like that, and that's what you think is driving the drought, you could do a scenario where you take your statistical model and then put, maybe you want to do a spatially smooth because you've got a fairly large area, do some sort of spatial layer of PET change, but do that as a scenario, say.
But isn't this just the delta method that you were talking about? So that's where I'm not.
It's kind of a hybrid, I think.
Well, that's what I'm.
It's kind of stopping short of applying the model to the data in 2050, for example.
Or rather, stopping short of giving that model any sort of special treatment. It's sort of saying, this is a scenario. Maybe this is a scenario based on several models in that sector, the warm, wet sector of the model space. I think what you want to stop short of is saying you've got 50 different, or 100, 200, in this case 235 different model scenarios out to the climate models out futures that we can look at, and then treating them as a probability distribution. But rather, you want to generate scenarios based on the broad messages that they're giving us, and where the region of risk lies.
I guess I want to stop short. I think it'd be wise to stop short of saying if you have 100 breeding ponds or suitable ponds for mallards currently, that you're going to have 73 in 2050. I'm not saying that you're going to say that, but that's too far. And you see it in habitat studies where they're like acreage of suitable habitat, and then look at the habitat, the acreage just completely shrink by 2050. And you're like, well, that's are you really understanding all the interactions and variabilities, issues that are going to come into it? Whereas,
I think from their perspective, it's they're basing management in this case is often the purchase of permanent conservation easements on wetlands and grasslands. And they're basing those based on today, where's the best habitat? And the question is, is the best habitat, is that good enough? Is that a robust strategy under climate change? And so that's what Susan was getting at, that why does it have to be spatially explicit? It's like, so what we just want to be able to say is, more, are those locations that are pretty good now going to continue to be relatively good in the future? And, and of course they are interested in some measure of, well, what's the percent change? I think that the management objective, there are like really defined objectives for the duck population, and there are other people sort of looking at that. I think from the surrogate perspective, it's, we're sort of interested in, are those relationships going to change? Like, if there are if the places that are good for ducks are also good for soras today, is that likely to continue to be true? So I think, I don't know.
It would be hard to give them a product without some kind of spatial.
But I think it's possible to create a map with a, uniform
PET change.
Yeah, with a uniform change, which is kind of like a scenario, and based on the work that from Andrea's colleagues, that's not unreasonable. And, I guess one question is, is it, how much easier is it, is I think another question, right? Is it, or, where's the trade-off or something? I don't know.
Let's go back and say, because one thing I think people don't know here is that the predictors you're using now there's one based on precipitation, one based on temperature, and then you wanted to add a drought-based indicator in addition to precipitation and temperature.
Yeah, and more than one, actually. I've looked at different seasonal relationships,
Right.
And then we also
I think you boil it down to maybe one or two.
Yeah, there's a few,
And we also have in the models land cover, and we also have in the models the wetland coverage is not how deep the water is, but just where the basins are. So those remain in the models, and those actually, according to Valerie's work, have shown that they are really important drivers in the system. It's just the land cover and the wetland basins, and then you overlay the climate on that, and it, there's some modifications. But
so let's say we're staying within the framework of a statistical model that you're using because you need to get your degree.
I have a degree, thanks.
Pardon me?
Luckily, I have a degree.
Oh, sorry. I thought you had to. This is your postdoc.
Yeah.
I'm sorry.
Yeah.
I thought you were just finishing. Could you?
So Valerie got to finish
this project.
degree or somebody.
No, we got to get Valerie.
Oh, I was confusing you two.
No, that's okay. No, it's no problem.
But there's a timeline with respect to kind of the management and the surrogate species decision in 2015.
Presumably, I'll still need another job.
Yeah.
Okay, you can just do the next one. But presumably, so you showed that PDSI was somewhat of an indicator of pond count. Although I noticed some interesting things in that time series too, like the fact that it was converging. And I think that indicates that some sort of drought index is a good surrogate for evaporative draw on these ponds, and therefore gives you your May pond count as not, as a response variable is not so bad. So I mean that gives you a logic of saying let's just do our best in coming up with with a regional scale, these are pretty regional scale, I suppose. I mean, the precip pattern can be pretty spotty, I suppose. That's the only problem with it, right? But so the problem with this is that you end up conflating precipitation into it, which can be very, very not regional.
Well, we can, you know, with this, we're putting together this drought index that's based on evaporative demand. It's called the Evaporative Demand Drought Index. You mentioned, funnily enough, or EDDI, that doesn't convolute precip into the index. It only looks at evaporative demand. And like Gabriel showed, negative anomalies in ET indicating drought, positive anomalies in evaporative demand also indicate drought. But I don't know how you push that out in the future, but if you only get two scenarios, it might be a worthwhile index to use.
So you could come up with some sort
And that's PDSI.
No, EDDI. EDDI.
only based on
we haven't,
evaporative demand,
yeah,
not on a compilation, not on a...
It's just American Society of Civil Engineers standardized reference ET. That's all it is. But it's a standardized anomaly.
And it's based on evaporative demand?
Yes.
Okay, so, because I thought he was pointing it, I'm
To
confused.
answer your question about availability, we haven't published on it. We're writing 2 papers that should be going in the next couple of months, but it's in use. Charlotte's using it for fire suppression cost estimation. But I can get it to you. I'm automating it now.
Right. Because that would be guaranteed, I would argue, in the climate models to have a larger spatial scale to it, so you wouldn't have to worry about the scale issue as much.
Yeah, but we might have to, does that mean we're going to have to persuade the managers that we picked an appropriate scale?
I'm not sure you mean, like, they don't expect us to be able to pinpoint, like, the conservation easements they should buy, you know? I mean, they're sort of interested in, is the Missouri-Coteau, which is in the western boundary of the PPR, kind of running through the center of the Dakotas, is that going to get too dry for ponds?
The Missouri...
It's like a hilly area in the middle of the Dakotas. Is that going to get too dry for ponds? Like, that's where the ponds are now. So there's some work that was really controversial that basically suggested that rather than investing there where the habitat's good now, you should invest further east because that's the only place there's going to be enough water later. But further east is totally agricultural. And so the cost of conservation is much higher because you have to do restoration, you have to, you know, the land has more value, et cetera, et cetera. So that's the scale that they're, you know, I think like the grain size of our analysis is pretty, like, you know, I don't think we need to justify that to them beyond that.
That's great, because we talked to some other people who want, you know, a pretty fine pixel.
Yeah.
Or they think they do. They may not have quite thought through.
But just a little bit of history that Helen was talking about. So a paper came out in 2010 that looked at the probable availability of waterfowl habitat relative to climate change. And the conclusion was all the waterfowl habitat is going to be in Iowa. So the people back in Washington, D.C. were saying to the land managers in Bismarck, North Dakota, why should we even give you any more money? All the waterfowl habitat is going to be in Iowa. This was a huge deal. So we're going to say, well, is it really true that all the waterfowl habitat is going to be in Iowa? And, you know, so we want to do it somewhat spatially explicitly, but also we're looking at, there's lots of other birds. There's 116 other species of water birds there that differ from the ducks. You know, what's going to be the importance across there. So in a way, we are almost asking, and it might have to be on a species-by-species level, is there a threshold in evapotranspiration whereby the wetlands that a given species is dependent upon dry too soon? And so it's no longer available to them. And there might be something whereby we can, with your data, ask that question over a 10-year time span with BVS data, maybe even duck nest survival data, and say, okay, in that 10-year period, if there are dry spells in there, is there a point, and then go and look for that point or have scenarios on one side or the other at that point. That's another
That's
approach.
another study.
Well,
Let me just say.
Yeah, but it could be
Yeah.
part of the
Yeah.
Jeff's scenario approach, where you go, let's have a scenario where it's wetter than that, and let's have a scenario where it's drier than
Maybe,
that.
maybe scenarios, maybe the wrong word. I'm kind of thinking like relative ranking given climate model projections, so that you've got, let's say, the strip along the current Missouri is one, right? Is best, and you could take optimal. You could put a threshold of optimal habitat currently, and then you could say, what are the multiple climate variables related to that optimal location, and then what's the change in those optimal climate variables in other locations, so that this one goes from optimal to becoming significantly less, but the eastern domain, those a handful of climate variables become better.
The problem there is that it's the reason it's optimal now, honestly, I think is because of the land cover and the topography. So that's one of the problems with that.
Yeah, but the land cover is going to be related to the climate, not the top.
Actually, we're collaborators.
Yeah, we're kind of working on that too with the collaborators.
I think getting, I think there may be two different issues here, and one of them that I think, Jeff, you're sort of talking about a lot is how do we characterize the uncertainty, essentially, and not avoid saying, oh, our result is this number, but I think it doesn't seem in opposition to, I guess, what maybe Joe and I as well were kind of assuming that we would do, which is run these models through the GCM projection and, figure out what are they saying, and then I sort of was envisioning that. How do we characterize the uncertainty as like a step following running these through with the GCMs, but I don't know.
If you look at in the unpublished manuscripts, if you look at the patterns of change in these drought indices that Seeger has calculated across there, which I think is a good qualitative indication of what these climate models are telling you, you do find different gradients across the region in terms of where it tends to get drier and wetter depending on the climate model scenario. And I think those are different possible futures that you need to talk about, right?
Well, and then I want to make a connection between this possible futures, range of possible futures idea and uncertainty. And is that what you mean by characterizing uncertainty?
The one component.
Yeah, I think that's a big piece of it.
Okay, yeah.
I think especially if you've moved to model space, then you're hoping that that's the biggest piece left, right? That seems to be the biggest advantage of that, is that it sort of isolates takes out everything except for the forcing, right? That's it, that was my takeaway in our email discussions of the big advantage.
Yeah, it's sort of a controlled, what we call numerical experiment, since we don't have wet labs, we have computers, right? So you got it exactly. It's a controlled setting in which only the forcing is changing. So you have to take that in context of everything else you know. And what Jeff is suggesting is, but you might lose some subtleties in the mechanisms in the present day by doing that. And by understanding those mechanisms and how things change in the present day and constructing some sort of scenario-based, which almost says, if we take a dry year, but what happens in a dry year, maybe we should make that more extreme. What would happen if that happened?
Yeah.
What would happen if we got 3 dry years in a row? I don't think these models are very time sensitive year to year.
I do have lag covariates, so I try to capture it that way, but they're not explicitly, AR1 models or AR whatever models.
One thing we know is that, let's go back to what we do know is that however we want to calculate some sort of evaporative driver, we're not going to use a temperature-based method. We're going to use something that involves more physics, probably some sort of Penman-Monteith-based calculation. And we have options here, and we have some options here, which we haven't really talked about.
So are we now moving into kind of a draft? Things
that Helen has already discovered,
yeah.
And I think through this discussion, is that
because we have about 10 minutes.
if you,
really finishing around 12:30.
Yeah,
if you're concerned about this area in the central Dakotas, and you're concerned it's a marginal dry, margins of dry and wet areas, and if you're concerned about that, you know, if you're concerned that this earlier study was too coarse that just said, well, it's going to warm up and dry up, because a lot of the physical models say, well, that might not quite happen, or at least not as fast as they think, if we put the correct physics in there. So it's imperative to use something that has the correct physical drivers of, let's just call it evaporative demand, or the evaporative demand component of these drought indices, right? So using something, and we now have several products that I think would, we have to look at the details of what years, but they could actually meet that. And I think as long as you do that, your statistical model will even out some of the differences, right?
Okay, and those several products would be the...
Well, the Seeger climate model derived one at 1 degree, the NASA, believe NASA Next has something like this.
So
But
it's not on their website, right? I mean,
Well, they
it's
said
not-
they had it in one of their documents, and I haven't found it yet. I looked
Okay,
last night.
because they have precip and temperature, you know, that's at a much finer spatial resolution.
The next 1 degree?
Next,
kilometer, but
4 kilometer and 800 meters. I think the 4 kilometers is where they ran to the TOPS model. We have other ones that we come up with at an 800 degree. The Bureau of Reclamation is going to publish some using the BCSD method. So that's doable, and the most important thing about that is you're using a physically based evaporative driver, because you really do need that in these marginal regions. I mean, if the question is whether those areas dry up, you better be getting the physics right. I would like you to sort of, I mean, that's critical, right? If you're in a sort of marginal, where the margin is moving, that's where you have to be most fastidious about the physical drivers, in my view. You have good relationships between these drought indices and your pond counts, so that's a nice indication that this is a valid predictor, and we should just do our best to make it as physically based as possible, so when we go up to the future, we get a good indication of what that is. So that much is sort of agreed upon.
So you're saying PDSI seems reasonable, but you just have to make it as physically based as you can.
M and Monteith-based PDSI is
Which the NASA Next data has.
I know, does it?
That's what you're saying the top product was, I thought.
I don't know. I'm pretty sure it is,
Okay.
but I have to check it. But I have to check where it is. They said,
Yeah.
I read in an article they said they were going to run this through and produce all this data, and I assumed that they had.
Okay.
And this is one of those things of just chasing down data sets.
Yeah.
I think we just need to call them up.
And sometimes you just want to bash your head against the
But we have
they actually write about their data.
so as far as coming up with a predictor,
bash their head against it.
and we might want to try a couple of these, but coming up with a predictor, I think we're fairly far along using in your models that we can use for historic. As long as you want to jump to model space, that's fine. If you want to do a delta-based method, which, we can talk about that later, I suppose.
My sense, like from our phone conversation, is that I might as well jump to model space, look at the distributions, and see if there's a big problem.
I think that's really seems like a necessary step.
Yeah. And I was thinking of looking at it over space as well, because there is that's sort of one of the important goals of our project. So, if the historical model projections don't see the Missouri Coteau, the good region, as a good region, then we have a big problem,
Right.
But
So, and they'll be bias corrected, so they should see a somewhat a good region, but maybe, I don't know how at all.
Yeah.
And since you don't have a lot of dependence from year to year, you might be okay. But I have to think, I mean, there's all sorts of things that can go wrong along the way. You just have to check. The second question that Jeff brought up is how to create a set of scenarios out of this that communicate well with stakeholders, really, and that don't over-communicate the precision, right?
Well, I guess, if you think of it as like habitat or, whatever your response variable is a function of, 5 variables. and then you only have 2 of those in the future, and they're much less certain. How do you do that? You fit the model with just those 2 variables, or, and I guess that's where we were with, kind of the thought is to say, do the best you can with 5 variables, have a map, and then say, we don't have future land cover, we don't have future variable 4 and 5, and then variables 1 and 2 of sort of drought and temperature, or some sort of climate-related variables. We have projections of those in the future, and there's much less certain, but this is the direction they go.
Yeah. And I think from the perspective of isolating the effect of climate change, I mean, that's all you can kind of do, right?
Yeah.
Like the land cover, we are working with someone that's modeling it. Frankly, I don't know how he's doing it because it totally depends on, like, corn subsidies, as far as I can tell, right?
And so are you going to try to either assume land cover is static and apply a model in 2050, or do some model of land cover, which is
that's what he is doing.
You can do, but then you're like, well, now your uncertainty becomes.
And true, there's economic aspects to it, but he is an economist, so hopefully he's got a way.
It's contingent on things that you could say. It's contingent on corn subsidies, right? It's contingent on things. So the way we deal with greenhouse gases.
Yeah, and so essentially what our plan is to take our future model and run it out into the future with a static land, and then with his predictions, and assess that as part of the uncertainty too. So I think it's like you get to this point, and I'm sure you guys have struggled with this some, where it's like then you have a bunch of raster layers, and you and the managers want a map, right? And so I think that's a challenge that you have, even if you're not dealing with climate change, even if you're just doing a bunch of different species distribution modeling methods or whatever.
You could kind of rank them, just the number that show consistency or something.
Yeah.
Kind of a crude way, and it can kind of be maybe. Anyway, so while we have other people here, the last question is, in these regions where we have these sensitive ponds, do we need to go and do a hydrologic modeling exercise that's specific to the ponds? And so we have, I don't know if Ben is still on the phone. Ben?
He signed off.
Okay.
I think Balaji's gone too.
Yeah.
On Sonic.
Well, we have Kyle, and hydrologic modeling is possible in many hydrologic models to put at least rudimentary wetland models in there. Is this something we should investigate, that I should investigate as climate team lead, as getting something spun up to do that in the future?
Gabe, are you familiar with Jennifer Rover's on this? Because she's kind of doing this, isn't she?
They do the surface area mapping of the wetlands, but I don't think they do a hydrological.
But that's what Carter Johnson.
Flex mapping, flex modeling of the wetland. They do surface area changes.
Yeah, so they're looking at basically percent full.
Shrinking and expanding.
Yeah, shrinking.
You can join that with a hydrological model, and then that includes probably regional groundwater, because some of them are, fed by regional groundwater, and whether the PET is very high, doesn't matter as long as there's a flow coming in.
Oh,
so I think it's very important to include the hydrological model.
Yeah.
Because, the PET is very high, but this, pond is being fed by regional water flow.
Although I think a lot of the waterfall in particular, are they using mostly the seasonal wetlands that are not connected
in
to
the first earlier stage.
Yeah, it depends on their hydrology.
Well, that's the controversial paper Susan was talking about earlier. It actually is a hydrological model. And part of the reason it's controversial is they just sort of ignored the reality of the distribution of wetlands on the ground when they said that Iowa was better, because there was really no wetlands there because it's all agricultural. But I think at some point we have to draw the line at what's reasonable, what's not. Maybe
if your statistical model works at the scales you need it, then that's really good for your study.
I feel like all the models have been talking about too, that using like PET or evapotranspiration and these sort of like atmospheric characterizations of drought makes the most sense for you, like modeling, sort of spatially modeling how ponds are going to shrink. I think that there's a compelling argument to be made for that. I think an eco-hydrological model doesn't suit your needs at all. So soil lot, while it could do something with the standing water cover, is really meant to model vegetation. So what we have you couldn't use, I think, to answer your question. Not to say their mechanistic model isn't appropriate, but the one I got, you can't use.
Yeah.
Yeah, we have plenty more territory in the North Central. Do you think we should go around before we quit here and just, anybody who wants to say anything? Is that, we really want to, wrap it up.
Yeah, let's just at least open it up to somebody who's got a comment or needs to feels want.
Well, yeah, I was just going to say then, if you don't do full hydrological model on the wetlands, at least you can look at the thermal-based data to see the drying cycle of the wetlands.
Yeah,
If you want more information without going through a full hydrological model. The timing, and just the nature of the wetland.
And you could build a statistical model on that
Right.
that you could then
yeah,
extend.
like a new response variable.
That you could extend to a far. That's really a great idea. Any other great ideas that have come up here? Or,
Well, what I was going to do is there's the revampcolostate.edu, revampclimate.colostate.edu, our webpage. If you do revamp NCCSC or just look that up, that's our website. Is have the presentations, agenda, and participants in this meeting. And it seems like there's a lot of connections that, maybe continue. But we've got the email. I think everyone's got everybody else's email just from what's been going around, so that, people can take a lot of this offline and continue the conversations.
and I think as this matures, as a couple of other projects mature, we should probably have Richard Seeger talk at one of our calls, and we should probably have Steve Running's group talk when they get the ET product produced.
That's a given, or I definitely would want to put them on the hook to do that.
And so keep in mind that there's two sources of information who are not at this table,
Right.
that are probably going to be part of the discussion in the future about various central projects.
So we're going to communicate this somehow? Is someone going to distill this list and say, okay, here's the products that we have available right now? Because I'd like to explore the data sets that we've talked about here, but I was kind of like, it was machine gun fire.
Oh, and I was trying to fill in lots of stuff last night, and I just don't even know where some of this stuff is,
Yeah.
So I'm going to work with Jeff and try and come up with the best place to put that.
We're going to table like you were showing?
Well, I mean, the table was just me organizing my thoughts.
Right. I find that a little bit. I think that would be, we could put it on the climate drivers website, revamp climate.
Some of these data sets are on this climatedataguide.org, which comes out of NCAR and a bunch of other people. And but there's often very sparse information on there. I know, Gabriel, you should put, if it's not on there already, you should put it there. It's just a nice place to organize a lot of information about this data. But I think we need stuff that's more specific to the North Central region. So we'll try and build some I think Jeff and I were talking about building some web pages on the revamp site.
Yeah, we got science base and other capacity at USGS, and we could just point to it to the CSU page. So, with Colin's help, we could kind of figure out what might make the most sense for putting this stuff.
Okay. So we'll try and come up with it. I can try and fill this out a little bit more and circulate it.
Did you say that website again? What was it?
It's called climatedataguide.org. And I have to admit, in the last year, it's really matured into a very nice site. A year ago, I wouldn't have recommended it. Now I do all the time. But we can't really use that because it's not really specific. We can use it for general information and encourage people to put stuff on there.
Yeah, we might put stuff on there, but we also want to have something that's for North Central.
That's a community site that you can actually comment on data sets there, although not that many people do. But I want to do something like that where I view it as part of one of my roles is to kind of just sort through all this stuff and give a sense of even just what's there, because sometimes the choice of data set, if it's not all that different, is determined by spatial coverage or by temporal coverage.
So are you then going to suggest, if we're moving to model space, what you recommend moving to model space with?
Not right now.
Yeah.
No, but is that on your list?
I think it's going to be sort of like what are you sacrificing when you go to this other data set because it has longer temporal coverage? How much really are you sacrificing by doing that? It's more going to be what the trade-offs are I don't think one data set covers everything, and that's what the issue is.
So the NASA next data don't go back to the mid-century?
Not that I know of. They go back, well, they go back to 1980, but they don't go back to I don't really know. Off the top of my head, I don't know where they went back to. They used...
I thought their temperature and precipitation data went too far back. So
I was thinking it was 1950, at least some of it
Yeah,
anyway.
me too.
I think it's... Anyway, it's one of those things where just a table of this stuff would be really useful for me, let alone for it's like I just can't keep all those kind of details. Of the data sets I'm intimately familiar with, I know them, but of the ones that are sort of at my...
How far back did Seeker go?
Well, I think he did the whole climate...
Yeah,
As far as I know, he did the whole climate runs, which was like 1850 to 2100, right on through.
Fake past, right? Like the
fake past, the
Simulated past, please.
the fake past,
Or faux, perhaps.
the faux past.
Faux.
Yeah, anyway, I don't want to, I just think this has been really, really great start, and part of this is just connecting experts available here to build just sort of a base of knowledge and people you can count on. So I think this.
Yeah, I appreciate everybody, Helen in particular, for throwing this together quickly. It was a whirlwind tour, and we didn't have much time to get into some pretty detailed and meaty topics, equations, algorithms, but there was pressing needs for them to have this kind of now, as opposed to a 2-day workshop in the fall, which we could contemplate, and we could think about as Joe gets a postdoc hired on, and we really think about this and maybe have some more results. We could certainly think about a 2-day kind of workshop, but let's appreciate the.
And Mike and I have some plans to explore a little bit more about what's driving the changes in the future in these models, and really which of these approximations work the best in which areas. So, but that's not going to happen in time for you to do what you're doing. I think exploring this, I think what you're doing is sound. I mean, I didn't want to say it right away. I wanted to have time to think about it and let other people think about it, because it's kind of a little bit new to use these PET-based predictors. So I wanted to have time to mull it over as a group.
Okay, good. Well, thanks everyone.